At night, the Milky Way looks endless, a pale band of light stretching across the sky, built from more stars than the human mind can comfortably hold. From Earth, it feels complete, not just large, but total, a structure so vast that it seems to define the limits of existence itself. And by everyday standards, it does. Light takes tens of thousands of years to cross the Milky Way. Hundreds of billions of stars move through its spiral arms. There is no visible edge from inside it, no natural way to sense its full shape. From within, it feels less like an object and more like a universe. But that impression does not survive distance. When astronomers first realized that other galaxies existed beyond the Milky Way, something quietly unsettling became clear. Our galaxy was not unique. It was not dominant. It was not even especially large. It was one example in a population so vast that individual galaxies begin to lose their identity when viewed on the larger scales. That creates a real paradox. How can something so large that it overwhelms human intuition be small enough to barely register in the universe as a whole? How can a structure that defines our entire sky become almost negligible when the view pulls back far enough? This is not a trick of language. It is a consequence of scale. The Milky Way is enormous in every meaningful human sense. It is also finite, limited, one structure embedded in something far larger, governed by rules that do not care where we happen to be standing. If that contradiction feels uncomfortable, it should. Astronomy does not exist to reassure. It exists to show what is actually there. In this video, the view slowly widens. The galaxy that feels endless begins to take on edges. The scale that once seemed absolute starts to shrink. Not because the Milky Way changes, but because the context does. If you want to see what happens when perspective keeps expanding and familiar scales quietly fall apart, subscribe to the Sleepy Astronomer and continue the journey. Size is something learned early, long before it is questioned. A room feels larger than a cupboard. A field feels larger than a room. A mountain feels larger than a field. Human intuition builds scale by stacking familiar experiences, one on top of another, each new size anchored to something already known. Distance is measured by walking, by driving, by watching landmarks slide past a window. Even large numbers feel manageable when they can be tied to time, effort, or movement. That intuition works remarkably well on Earth. It begins to struggle the moment the sky is involved. The moon already breaks the system. It looks close enough to touch, yet it is far enough away that every human who has ever lived could fit inside the gap between Earth and its surface with room to spare. The sun stretches intuition further still. Light, the fastest thing known, takes minutes to reach Earth from its surface. Already, everyday experience has lost its grip. And yet, these are still local distances. The Milky Way sits far beyond anything human intuition evolved to handle. It is not just larger than planets or stars, it is larger than time-bound thinking itself. Light does not take minutes or hours to cross it. It takes tens of thousands of years. A signal leaving one edge of the galaxy would still be travelling long after every city on Earth had turned to dust. From within, this scale feels overwhelming. The Milky Way arches across the night sky as a continuous presence, a luminous band that suggests depth without revealing boundaries. There is no horizon line to mark where it ends, no edge to signal completion. For observers on Earth, the galaxy feels less like an object and more like an environment. This sensation is not an illusion. It is a direct consequence of perspective. Human perception evolved to navigate landscapes measured in footsteps and days. It did not evolve to grasp structures made of hundreds of billions of stars bound together by gravity. When the brain encounters scales that large, it substitutes feeling for understanding. Vastness becomes a sensation rather than a quantity. Immensity becomes emotional rather than numerical. This is why knowing a number is not the same as grasping scale. It is possible to say that the Milky Way contains hundreds of billions of stars and feel almost nothing in response. The words pass through the mind cleanly, neatly, without resistance. But attempting to imagine even a fraction of that number as individual objects quickly collapses into abstraction. The mind stops counting and starts gesturing instead, replacing comprehension with awe. Ancient thinkers noticed this tension long before telescopes existed. Philosophers like Aristotle argued that the cosmos must be finite, partly because an infinite universe seemed incompatible with human reason. Later thinkers such as Immanuel Kant wrestled with the opposite problem, realizing that both a finite and infinite universe produced contradictions when pushed far enough. The issue was never just astronomy. It was cognition. How a limited mind confronts unbounded scale. Modern astronomy does not resolve this tension. It exposes it. The Milky Way is structured, measurable, and governed by physical laws. It has a disk, spiral arms, a central bulge, and a vast halo dominated by dark matter. These are not poetic descriptions. They are physical components inferred through observation, motion, and radiation across the electromagnetic spectrum. The galaxy is a gravitational system with a definable mass and a describable shape. But none of that makes it intuitive. From inside the Milky Way, every star appears pinned to the same sky, regardless of its true distance. Nearby stars and distant stars share the same darkness. Depth must be reconstructed indirectly through careful measurement, using methods like stellar parallax and standard candles. Without these tools, the galaxy collapses into a flat illusion, its true size hidden by perspective. This is where human perception reaches its limit. Distance stops feeling like distance and becomes something else entirely. Time becomes entangled with space. A journey across the galaxy is no longer a matter of travel, but of eras. Entire evolutionary histories fit inside the time it takes light to cross the galactic disk. The scale ceases to be navigational and becomes historical. There's also an emotional shift that comes with this realization. On Earth, large things feel dominant, mountains impose themselves, oceans demand respect. In the galaxy, size does not behave that way. Immensity becomes quiet. The Milky Way does not press inward. It surrounds without weight. It feels vast without feeling oppressive, simply because it is too large to register as a threat. This can be strangely disorienting. Something so large that it defines the night sky should feel absolute, final. And yet astronomy quietly suggests otherwise. The galaxy is not the largest structure in existence. It is not even close. It only feels complete because everything familiar happens inside it. This is the subtle trap of intuition. It confuses enclosure with totality. Early cosmological ideas often placed humanity at the center of everything, not out of arrogance, but out of necessity. Without evidence to the contrary, the visible sky felt like the whole. Even now, despite centuries of observation, the mind continues to default to the largest structure it can emotionally register and treat it as a boundary. The Milky Way occupies that role today. It is the largest thing most people ever meaningfully encounter, larger than any planet, any star, any lifetime. It becomes the final scale by default, not because it is final, but because it is where intuition gives up. Understanding this does not reduce wonder, it sharpens it. The galaxy's vastness is real. Its scale is not exaggerated by perception. What changes is its status. Once size becomes something that can be measured rather than felt, the Milky Way begins to shift from being the ultimate container to being one structure among many. That transition is not immediate. It unfolds slowly as perspective widens and familiar anchors disappear. The mind resists at first, not because the information is wrong, but because the scale is incompatible with instinct. This resistance is not a failure, it is the starting point. Astronomy begins here, at the edge of intuition, where numbers stop meaning what they usually mean, and where size becomes something that must be approached indirectly. The Milky Way stands precisely at that boundary, large enough to overwhelm the mind, small enough to eventually be placed inside something larger. And it is this tension between what feels infinite and what is merely vast that quietly reshapes how size itself is understood. The word galaxy sounds abstract, but it describes something very specific. A galaxy is a vast gravitationally bound system made of stars, stellar remnants, gas, dust, and a dominant but invisible component known as dark matter. Everything inside it is held together by gravity, moving as part of a single structure rather than drifting independently through space. Stars orbit a common center. Gas clouds collapse and form new suns. Ancient stellar remnants continue their slow paths long after their light has faded. The Milky Way fits this definition precisely. It is not a loose collection of stars scattered at random. It is a coherent system with structure, history, and internal motion. Every visible star in the night sky belongs to it, with only a few rare exceptions far beyond our galaxy. From Earth, the Milky Way is not something looked at from the outside. It is something lived inside. This inside perspective shapes everything that is seen. The Milky Way contains several broad populations of stars, each telling part of its story. Near its centre and within its thick disk are older stars, many formed when the galaxy itself was young. These stars tend to contain fewer heavy elements because they formed before multiple generations of stellar birth and death enriched the galaxy with heavier material. Farther out, in the thinner disk and spiral arms, younger stars dominate, often accompanied by glowing clouds of gas and dust where new stars are still being born. Gas and dust play a quieter but essential role. Vast clouds of hydrogen drift through the galaxy, sometimes remaining diffuse for millions of years, sometimes collapsing under gravity to ignite new stars. Dust grains, though sparse, shape how the galaxy appears by absorbing and scattering light. Entire regions of the Milky Way are hidden behind these dark lanes, not because they are empty, but because their light never reaches Earth. Then there is dark matter. It does not emit light. It does not absorb light. It does not interact with normal matter in ways that make it directly visible. And yet, its presence is unmistakable. The outer regions of the Milky Way rotate far faster than they should if only visible matter were present. Stars orbit the galaxy as if wrapped in a massive invisible halo. Without dark matter, the Milky Way would not hold together in its current form. This realization emerged in the 20th century through careful measurements of galactic rotation. Astronomers such as Vera Rubin demonstrated that the observed motion of stars could not be explained by visible mass alone. The galaxy, it turned out, was far heavier than it looked. The Milky Way's shape reflects this hidden structure. It is classified as a barred spiral galaxy. A dense central bulge of stars surrounds a supermassive black hole, while a bar-shaped concentration of stars extends outward before giving rise to spiral arms. These arms are not rigid structures, they are regions of higher density, where stars and gas move in and out over time, like traffic slowing along a curved highway. The spiral arms host many of the galaxy's youngest stars. Bright, short-lived suns light up these regions, tracing the arms in luminous arcs. Between them lie darker interarm spaces, still rich with stars but less visually striking. The overall disk is thin compared to its width, extending far across space while remaining relatively flat. Surrounding all of this is the galactic halo, a vast, roughly spherical region populated by older stars, globular clusters, and the bulk of the galaxy's dark matter. The halo extends far beyond the visible disk, blending gradually into intergalactic space. There is no sharp boundary where the Milky Way simply ends. Gravity is the thread that binds all of this together. Every star in the Milky Way follows a curved path shaped by the combined gravitational pull of everything else. The galaxy does not spin like a solid object. Different regions rotate at different speeds, governed by how mass is distributed. This motion is orderly on large scales yet complex in detail, shaped by past mergers, interactions, and internal dynamics, stretching back billions of years. Without gravity, the Milky Way would not exist as a galaxy at all. Its stars would drift apart, its gas would disperse, and its structure would dissolve. Gravity gives the galaxy both its form and its longevity. From Earth, however, none of this structure is immediately obvious. The Milky Way appears as a glowing band across the sky because the solar system sits inside the galactic disk. When looking outward along the plane of the disk, the line of sight passes through enormous numbers of stars. Their combined light blends together, forming a soft, continuous glow. When looking away from the disk, fewer stars lie in that direction, and the sky appears darker. This band is not uniform. It is brighter toward the galactic center, where stars are more densely packed, and fainter toward the outer regions. Dark streaks cut through it where dust blocks starlight. Subtle variations trace the underlying structure of the galaxy, though they are easily missed without careful observation or truly dark skies. For most of human history, this appearance was deeply mysterious. The Milky Way was once thought to be a cloud, a river of light, or a seam in the heavens. It was not until the work of astronomers like Galileo Galilei that its true nature began to emerge. When Galileo turned a telescope toward the Milky Way, he found that its glow resolved into countless faint stars, each too dim to be seen individually with the naked eye. Even then, the full implication took centuries to unfold. It was not until the early 20th century that astronomers confirmed the Milky Way was just one galaxy among many. Observations of distant spiral nebulae, combined with distance measurements using Cepheid variable stars, revealed that these objects lay far beyond the bounds of our own galaxy. The Milky Way was no longer the entire universe. It was a single structure within a much larger one. This realization reshaped how the galaxy itself was understood. Once the Milky Way was recognized as a galaxy, it became possible to study it using the same physical principles applied elsewhere. Stellar evolution, gas dynamics, gravitational collapse, and orbital motion all operate within it according to the same laws seen throughout the universe. The galaxy is not a special case. It is an example. Yet it remains difficult to see clearly, precisely because it is home. Mapping the Milky Way requires indirect methods. Radio observations trace hydrogen gas across vast distances. Infrared telescopes peer through dust that blocks visible light. stellar motions reveal gravitational influences that cannot be seen directly. Piece by piece, a picture emerges, never complete, always improving. There are still uncertainties. The exact shape of the spiral arms is debated. The full extent of the dark matter halo remains unclear. The history of past mergers with smaller galaxies is still being reconstructed from faint streams of stars arcing through the halo. The Milky Way is known, but not fully known, and that incomplete knowledge is not a weakness. It reflects the scale of the object being studied. The Milky Way is not something that fits neatly into a single image or description. It is a dynamic system unfolding over billions of years, shaped by processes that are still active today. Stars continue to form, orbits continue to evolve, the galaxy continues to change, even as it appears stable on human timescales. From inside it, the Milky Way feels vast, enclosing, and almost total. From the outside, it is one spiral galaxy among many, governed by the same rules and subject to the same limitations. Both views are accurate, neither is complete on its own. Understanding what the Milky Way actually is means holding these perspectives together. A single, gravitationally bound system made of stars, gas, dust, and dark matter. A luminous band across the night sky. A complex structure shaped by gravity and time. And a reminder that even the largest familiar structures are only part of a much larger whole. Understanding the Milky Way is difficult for a simple reason. Everything happens from the inside. There is no distant vantage point from which its full shape can be seen. No external camera pulling back to reveal neat spiral arms and clean boundaries. Every measurement must be inferred indirectly, reconstructed from countless local observations stitched together across space and time. Astronomers are not mapping a landscape from above. They are navigating it from within, surrounded on all sides. This makes the Milky Way fundamentally different from almost every other object studied in astronomy. When a distant galaxy is observed, its overall structure can be captured in a single frame. Its rotation, brightness, and shape are immediately visible. The Milky Way offers none of that clarity. Its stars surround the observer. Its dust blocks large portions of its own light. Its true size and form must be deduced rather than seen. The challenge is not a lack of data, it is perspective. Distance is the central problem. On Earth, distance can be estimated by motion and parallax without much thought. Nearby objects shift position as an observer moves, while distant ones remain fixed. This same idea applies to the stars, but at vastly reduced scales. The apparent shift of even the nearest stars against the background sky is extraordinarily small. This effect, known as stellar parallax, was first proposed in ancient times and measured successfully only in the 19th century. By observing a nearby star from opposite sides of Earth's orbit around the Sun, astronomers can detect a tiny angular shift in its apparent position. From that shift, distance can be calculated using geometry. The principle is simple, the execution is not. Even the closest stars show parallax angles so small they push the limits of precision. Beyond a few thousand light years, the method becomes ineffective. The galaxy extends far beyond that range. New tools are required. This is where stars themselves become measuring instruments. Certain stars change brightness in a regular, predictable way. These variable stars pulse, growing brighter and dimmer over fixed intervals. Among the most important of these are Cepheid variable stars. Their significance lies not in their variability alone, but in a relationship between how bright they truly are and how quickly they pulse. This relationship was discovered by Henrietta Leavitt in the early 20th century. While studying variable stars in nearby galaxies, she noticed a precise connection between the period of a Cepheid's brightness changes and its intrinsic luminosity. The longer the pulse, the brighter the star truly is. This insight transformed astronomy. Once a Cepheid's true brightness is known, its distance can be calculated by comparing that brightness to how faint it appears from Earth. These stars became standard candles, objects of known luminosity used to measure vast distances across space. Where parallax failed, Cepheids succeeded. Using Cepheid variables, astronomers began to map the structure of the Milky Way more reliably. Star clusters could be placed at known distances. Spiral arms could be traced indirectly. The position of the galactic center could be inferred even though it lay hidden behind thick clouds of dust. Still, much of the galaxy remained invisible. Dust absorbs and scatters visible light, especially along the dense plane of the galactic disk. Entire regions disappear behind dark veils. Optical telescopes see only fragments of the full picture. To see farther, astronomers had to stop relying solely on visible light. Radio astronomy opened a new window. Neutral hydrogen gas, the most abundant element in the Milky Way, emits radio waves at a very specific wavelength. These waves pass easily through dust, allowing astronomers to map hydrogen clouds across the galaxy. By measuring the motion of this gas through Doppler shifts, it became possible to trace the spiral structure of the Milky Way in 3 dimensions. This approach revealed something subtle and important. The galaxy is not a rigid object with clearly defined arms frozen in place. Its spiral structure is dynamic. Gas and stars move through regions of higher density, compressing and expanding as they orbit the galactic center. The arms are patterns, not permanent fixtures. They persist, but they are not made of the same stars forever. Radio observations also provided strong evidence for the galaxy's mass distribution. Stars and gas orbit the center of the Milky Way at speeds that cannot be explained by visible matter alone. The outer regions move far too quickly to be held together by stars and gas. This discrepancy pointed toward the presence of a massive unseen halo surrounding the galaxy. Dark matter became an unavoidable conclusion, not a speculative one. Despite these advances, uncertainty never disappears entirely. Distances measured using standard candles rely on careful calibration. Cepheid variables themselves must be understood precisely. Their behavior can vary slightly depending on composition and environment. Errors compound as measurements extend farther outward. Small uncertainties close by become large uncertainties at galactic scales. Even the Sun's exact distance from the galactic center has been refined repeatedly over time. The difference may seem minor on paper, but it alters calculations of orbital speed, mass distribution, and overall size. Each improvement sharpens the picture while reminding astronomers how delicate the measurements are. Modern missions have improved matters significantly. Space-based observatories have measured stellar positions and motions with unprecedented accuracy, tracking tiny shifts across the sky over many years. Millions of stars now have well-defined distances and velocities. Patterns emerge from this data, revealing streams of stars left behind by ancient galactic mergers and subtle ripples caused by gravitational interactions. And still, the map is incomplete. The far side of the galaxy remains harder to study than the near side. Dust continues to obscure key regions. The dark matter halo cannot be seen directly, only inferred from motion. The exact shape and extent of the Milky Way's outer boundaries remain matters of active research rather than settled fact. This persistent uncertainty is not a failure of science. It is a consequence of scale. The Milky Way is not an object observed briefly from afar. It is a structure tens of thousands of light-years across, studied from a single moving point embedded deep within its disk. Measurements take decades. Models evolve slowly. Confidence builds through accumulation rather than revelation. There is also a deeper reason why uncertainty remains. Galaxies are not static. The Milky Way is still forming stars. It is still absorbing smaller galaxies. Its structure continues to evolve. Any map is a snapshot taken during a process that spans billions of years. Precision does not freeze motion. It simply describes it more accurately. In this sense, measuring the Milky Way is less like measuring a building and more like measuring a storm from inside the clouds. Patterns can be identified, forces can be described, boundaries can be estimated, but absolute certainty remains just beyond reach. That limitation carries a quiet significance. The inability to see the Milky Way whole is not merely a technical challenge, it is a reminder of position, of scale, of the difference between inhabiting a structure and observing it from outside. The galaxy resists simplicity not because it is mysterious by design, but because it is large enough to exceed direct experience. Every method used to measure it, from parallax to variable stars to radio mapping, is an attempt to compensate for that limitation. Each succeeds within bounds. None offers a complete view on its own. Taken together, they reveal something remarkable. The Milky Way can be measured, its size can be estimated, its mass can be constrained, its structure can be traced, and yet it never becomes fully familiar. It remains partly inferred, partly reconstructed, and partly unknown. That combination is not accidental. It is what happens when a mind evolved for short distances tries to understand a system measured in tens of thousands of light-years. The galaxy can be known but not seen, and that distinction matters. Asking how big the Milky Way really is sounds like a straightforward question. It is not. The difficulty does not come from a lack of measurement, but from deciding what is being measured in the first place. The Milky Way does not have a hard edge. It does not end the way a continent ends at a shoreline. Its matter thins gradually, fading into regions where belonging becomes a matter of definition rather than visibility. Still, there are ways to describe its scale. When astronomers speak about the size of the Milky Way, they often begin with its disk, the flattened region where most of its stars reside. From one side to the other, this disk spans roughly 100,000 light-years. That distance is already far beyond everyday comprehension. Light, moving at the fastest speed allowed by the universe, would take 100,000 years to make the crossing. Human history, agriculture, cities, and writing all fit comfortably into a fraction of that time. Even this comparison fails to capture the experience of the distance. A light-year is not a measure of time in this context, but of space. It represents how far light travels in a single year, moving continuously without slowing or stopping. Saying 100,000 light-years is less a number than a statement about scale. It means that the Milky Way is large enough that cause and effect are separated by epochs. The disk itself is thin compared to its width. Measured from top to bottom, the visible stellar disk is only a few thousand light-years thick. Most of the stars occupy a relatively narrow band, orbiting the galactic center in a flattened arrangement. From inside this disk it feels expansive and enclosing. From the side it would appear surprisingly slender, like a vast but delicate structure stretched across space. Above and below this disk lies something larger and more diffuse. Surrounding the Milky Way is a halo of stars and globular clusters, extending tens of thousands of light-years in all directions. These stars do not follow the orderly rotation of the disk. Their orbits are tilted, elongated and varied, suggesting a long history of gravitational interactions and mergers. The halo is sparse, but it is extensive, reaching far beyond the region where most stars are found. And beyond the halo of stars lies the most dominant component of all. Dark matter does not glow. It does not trace neat shapes in the sky, yet it defines the true extent of the Milky Way's influence. The dark matter halo stretches far beyond the visible galaxy, perhaps several times wider than the stellar disk. Its presence is inferred through motion. Stars and gas orbit faster than visible matter alone would allow. Something massive surrounds them, shaping their paths. This is where the idea of size becomes slippery. If the Milky Way is defined by where stars are visible, its diameter is about 100,000 light-years. If it is defined by where its gravity dominates, its reach is far greater. Objects can orbit the Milky Way at distances where almost no stars remain, held in place by an invisible mass that extends deep into intergalactic space. So which boundary matters? The spiral arms offer another perspective on size. These arms are not rigid structures, but regions where stars and gas are more densely packed. They wind outward from the central bar, curving gently as they trace the galaxy's rotation. The arms host many of the galaxy's brightest and youngest stars, making them visually prominent even though they contain only a fraction of the total stellar population. Between the arms, stars are still present, but less concentrated. The galaxy does not end where the arms fade. They simply lose definition, blending into a broader disk of older stars. This again complicates the idea of an edge. The Milky Way does not stop. It thins. The central region adds further scale. At the heart of the galaxy lies a dense bulge of stars surrounding a supermassive black hole. This region is tightly packed, dynamic, and ancient. Orbits here are shorter. Gravity is stronger. The density of stars increases dramatically compared to the outskirts. And yet, this intense core occupies only a small fraction of the galaxy's total volume. Most of the Milky Way's space is not crowded at all. Even within the disk, stars are separated by vast distances. On average, neighbouring stars are several light-years apart. Space dominates matter. The galaxy's enormous size does not come from being tightly packed, but from being sparsely populated across an immense volume. This sparsity is easy to miss when thinking in terms of numbers. Hundreds of billions of stars sounds crowded. Spread across 100,000 light-years, it is anything but. The Milky Way is mostly empty space, structured by gravity rather than filled by matter. Its size is not the result of accumulation alone, but of expansion guided by motion and time. Dark matter reinforces this picture. The galaxy's gravitational influence extends well beyond where stars shine. Dwarf galaxies orbit the Milky Way at distances far outside the visible disk, bound to it by gravity alone. Streams of stars arc through the halo, remnants of smaller galaxies torn apart long ago. These features trace the true reach of the Milky Way more accurately than light ever could. Yet even here, uncertainty remains. The exact size of the dark matter halo is still being refined. Its outer boundary is not sharply defined. Gravity weakens gradually with distance, blending the Milky Way's influence into that of the surrounding cosmic environment. At some point, it becomes ambiguous whether an object belongs to the Milky Way or merely passes nearby. This ambiguity is unavoidable. Galaxies are not isolated islands floating in empty space. They exist within larger structures, interacting with neighbours, exchanging matter, and sharing gravitational environments. The Milky Way's size depends not only on its own mass, but on its relationship with nearby galaxies and the broader cosmic web. Even the term diameter carries assumptions. A circle has a clear center and edge. The Milky Way does not. Its shape is asymmetric. Its mass distribution is uneven. Its outskirts are shaped by ancient collisions and ongoing interactions. Any single number describing its size is an approximation, useful but incomplete. And yet, those approximations still reveal something remarkable. The Milky Way is large enough that light struggles to cross it. Large enough that stars born on opposite sides will never meaningfully influence one another. Large enough that entire civilizations could rise and fall many times over before signals traverse its full width. At the same time, it is small enough to be contained within larger structures, small enough to orbit alongside other galaxies, small enough to be one filament in a vast cosmic network that stretches far beyond it. This is the quiet tension at the heart of the question. How big is the Milky Way really? It is big enough to overwhelm intuition, big enough to feel complete from within, big enough that its internal distances challenge the limits of imagination, and yet its size depends entirely on perspective. Defined by stars, it is vast. Defined by gravity, it is larger still. Defined by the universe around it, it is only one structure among many, with no special boundary marking where it truly ends. The Milky Way does not offer a single answer to the question of size. It offers a range shaped by how deeply one chooses to look and what one chooses to count. That is not a flaw in measurement. It is a reminder that in astronomy, scale is not just a number, it is a relationship. The Milky Way is often described as being full of stars, but that phrase hides as much as it reveals. Astronomers estimate that the galaxy contains on the order of hundreds of billions of stars. The exact number is uncertain, and that uncertainty is real rather than careless. Stars are not evenly distributed. Many are faint beyond easy detection, and large regions of the galaxy are obscured by dust. Every estimate depends on assumptions about what cannot be seen as much as what can. When surveys count stars in one region and extrapolate outward, small errors grow quickly. A slight misjudgment in stellar density or brightness can translate into billions of stars when scaled up to galactic size. As a result, estimates range widely, not because astronomers disagree on fundamentals, but because the object being counted is vast, uneven, and partially hidden. Even so, the number is staggering. Hundreds of billions of stars means hundreds of billions of individual nuclear furnaces, each following its own life cycle. Some are small and dim, burning fuel slowly for trillions of years. Others are massive and brilliant, living fast and dying young in spectacular explosions. Together, they form a population with immense variety rather than uniform repetition. Most stars in the Milky Way are smaller than the Sun. Red dwarf stars dominate by number. They are cool, faint, and long-lived, consuming their fuel so slowly that many formed early in the galaxy's history are still shining today. Individually, they are unimpressive. Collectively, they account for a large fraction of the galaxy's stellar mass and light over cosmic time. Larger stars are rarer. Sun-like stars occupy a middle ground, stable for billions of years, capable of supporting planetary systems with long-term energy sources. More massive stars are fewer still. They burn hot and bright, live for only millions of years, and end their lives as supernovae, enriching the galaxy with heavier elements. This range of stellar types means that the Milky Way is not static. Stars are constantly being born and dying. Gas clouds collapse under gravity to form new stars, while older stars exhaust their fuel and fade into remnants such as white dwarfs, neutron stars, or black holes. the galaxy's star count changes slowly over time, shaped by this continuous cycle. Where stars are found matters as much as how many there are. Near the center of the Milky Way, stars are packed far more densely than in the outer regions. Distances between neighboring stars shrink dramatically. In these central zones, the night sky from any hypothetical planet would be crowded with brilliant points of light. Orbits are faster. Encounters between stars are more common. The environment is dynamic and intense. Farther out, conditions change. In the outer disk, stars are spread more thinly. Distances of several light years between neighbors are typical. The sky grows darker between stars. Gravitational interactions are gentler. This is the region where the Sun resides, orbiting the galactic center at a comfortable distance, neither too crowded nor too sparse. The Sun's position is not central. It lies well away from the galactic core, roughly 2/3 of the way out from the center to the edge of the stellar disk. This location places it between spiral arms, in a region with moderate stellar density. It is not a privileged position, but it is a relatively calm one. Supernovae are less frequent here than closer to the core, and gravitational disturbances are less severe. This placement influences how the galaxy appears from Earth. From this vantage point, looking toward the center means looking into a dense forest of stars, gas, and dust. Looking outward means peering into thinner regions where stars are fewer and more widely spaced. The Milky Way's band across the sky is brighter and more complex in some directions than others, reflecting this uneven distribution. Despite the immense number of stars, space remains overwhelmingly empty. This is one of the most counterintuitive aspects of galactic scale. Even in regions considered dense by astronomical standards, the distances between stars are enormous. If the Sun were the size of a grain of sand, the nearest star would be kilometers away. Planets, moons, and debris occupy tiny volumes compared to the vast gaps between them. The galaxy's fullness is statistical, not spatial. Stars fill the Milky Way in the sense that there are many of them, not in the sense that they occupy most of its volume. The galaxy is dominated by space rather than matter. Gravity links objects across that emptiness, but the emptiness itself remains. This uneven filling is shaped by history. The Milky Way did not form all its stars at once. It grew over billions of years, absorbing smaller galaxies, forming new stars in waves, and redistributing matter through gravitational interactions. Some regions became rich in stars early. Others remained sparse. The present distribution reflects that long, uneven process. Spiral arms highlight this contrast. These regions host many young, bright stars that make them stand out visually. They give the impression of concentration and abundance, yet they represent only a fraction of the galaxy's total stellar population. Most stars belong to the older disk and halo populations, quietly orbiting without drawing attention to themselves. There is also a population of stars that is almost never seen directly. Brown dwarfs, objects too small to sustain full nuclear fusion, drift through the galaxy in large numbers. They emit little light and are difficult to detect. Their presence adds to the uncertainty in star counts, reminding astronomers that even hundreds of billions may be an incomplete tally. All of this contributes to a subtle shift in perspective. The Milky Way is often imagined as a crowded place, teeming with stars packed shoulder to shoulder. In reality, it is a vast structure where stars are rare points, separated by enormous distances, bound together not by proximity but by gravity, acting across emptiness. This is why the galaxy can feel full and empty at the same time. Full because it contains more stars than can be intuitively grasped. Empty because those stars occupy such a small fraction of its volume that space itself dominates the experience. Both impressions are accurate depending on which aspect is considered. The Sun's quiet orbit through this environment is part of that balance. It travels through a region where stars are neither scarce nor overwhelming, circling the galactic center over hundreds of millions of years. Its journey is unremarkable on cosmic scales, yet it takes place within a structure so large that the full orbit spans a significant fraction of Earth's biological history. Seen this way, a galaxy full of stars is not a crowded object, but a delicate one. Its scale comes not from density, but from reach, from the sheer volume over which gravity organizes matter into patterns that persist for billions of years. The stars give the Milky Way its light and character, but it is the space between them that defines its true size, and that contrast between abundance and emptiness is one of the galaxy's most enduring and quietly unsettling features. The Milky Way does not sit still. Every star, every cloud of gas, every grain of dust is in motion, bound together by gravity and carried along in a vast, slow rotation around the galactic center. From Earth, this motion is impossible to feel. The night sky appears fixed and unchanging, but beneath that stillness lies a constant, orderly movement on a scale that dwarfs anything experienced in everyday life. The galaxy rotates as a whole, though not like a solid object. Stars closer to the center orbit more quickly, while those farther out move more slowly, guided by the distribution of mass throughout the galaxy. The motion is governed by gravity alone. There are no rigid arms pulling stars along, no central axle driving the spin. Each star follows its own curved path, responding to the combined gravitational pull of everything else. The Sun is part of this flow. It travels around the galactic center at a speed of hundreds of kilometers per second, completing a single orbit in roughly 220 million years. This timescale is sometimes called a galactic year. Earth has completed many revolutions around the Sun during human history. The Sun itself has completed only a small number of revolutions around the galaxy since complex life appeared. This long orbit reshapes perspective. Civilizations rise and fall in the blink of a galactic eye. Continents drift. Species emerge and vanish. All of it unfolds while the solar system traces a gentle arc through the Milky Way's disk, maintaining its place within the broader structure. This motion is not perfectly smooth. As the Sun orbits, it passes through spiral arms, regions where gas and stars are more densely packed. These crossings may influence star formation rates nearby and alter the galactic environment slightly, though the effects are subtle and spread over immense spans of time. The journey is steady, not dramatic. Understanding this motion requires careful observation. Astronomers measure how stars move toward or away from Earth by studying shifts in their light. These shifts reveal velocities along the line of sight, combined with measurements of position and proper motion across the sky. They allow the reconstruction of stellar orbits throughout the galaxy. When these motions are mapped, a striking pattern emerges. Stars far from the galactic center orbit at nearly the same speed as those much closer in. According to classical expectations based only on visible matter, orbital speed should decrease with distance, much like planets orbiting the Sun. But the Milky Way does not behave that way. Something unseen is exerting influence. This discrepancy became clear in the 20th century when astronomers began measuring galactic rotation curves in detail. The outer regions of galaxies, including the Milky Way, move too quickly to be held together by the gravity of stars and gas alone. If only visible matter were present, the galaxy would fly apart. It does not. The most consistent explanation is the presence of dark matter, an invisible form of mass that surrounds the galaxy in a vast halo. Dark matter does not emit or absorb light, but it responds to gravity and exerts gravitational influence. Its distribution shapes the motion of stars across the Milky Way. The concept of dark matter emerged not from theory alone, but from motion itself. Careful measurements of stellar velocities revealed a mismatch between what could be seen and what had to exist. Observations by astronomers such as Vera Rubin played a key role in establishing that this pattern was not an anomaly, but a fundamental feature of galaxies. Motion in this sense becomes a form of vision. Even when matter cannot be seen directly, its presence can be inferred from how other objects move. The Milky Way's rotation reveals the shape and extent of its gravitational field, far beyond the visible disk. Stars and gas trace invisible contours, outlining a structure that light alone cannot show. This indirect view is essential. The galaxy's spiral arms are defined as much by motion as by appearance. Stars drift into and out of these regions over time. The arms persist as patterns of higher density rather than fixed collections of stars. Without studying motion, the arms would appear static and misleading. The central region tells a similar story. Stars near the galactic core move rapidly, influenced by a dense concentration of mass. Their orbits reveal the presence of a supermassive black hole at the center of the Milky Way, detected through the precise tracking of stellar motion over many years. Again, movement provides information where direct observation falls short. Even the halo participates in this dance. Stars far above and below the galactic disk follow elongated, tilted orbits, relics of ancient mergers and interactions. Streams of stars arc through space, the remnants of smaller galaxies torn apart and absorbed by the Milky Way. Their motion preserves a record of events long past. The galaxy's motion is not chaotic. On large scales, it is remarkably stable. The Milky Way has maintained its overall structure for billions of years, despite constant internal movement. Gravity acts as a unifying force, smoothing out disturbances and preserving order across immense distances. Yet this stability should not be mistaken for stillness. The galaxy is alive with motion at every level. Stars orbit, gas flows, spiral patterns shift, satellite galaxies circle and slowly merge. The Milky Way is a dynamic system, evolving continuously, even as it appears unchanged on human timescales. There is something quietly unsettling about this realization. From Earth, the sky feels fixed, almost eternal. Constellations seem permanent. The Milky Way arches overhead night after night, unchanged by human activity. But in reality, every point of light is in motion, every pattern temporary, every configuration a moment in a long sequence. The scales involved make this motion difficult to feel. Movements that reshape the galaxy take millions of years to become noticeable. Changes unfold too slowly for direct experience. Understanding them requires abstraction, patience, and trust in measurement. This is where astronomy departs from intuition. The Milky Way's motion cannot be sensed. It must be inferred. It is known through careful observation, repeated measurement, and the consistent application of physical laws. What cannot be felt is nevertheless real. In this way, motion becomes a guide to structure. By watching how stars move, astronomers uncover the galaxy's mass, its hidden components, and its history. The Milky Way reveals itself not through still images, but through trajectories traced over time. The galaxy is not a static backdrop to existence. It is a system in motion, carrying the Sun, the Earth, and everything familiar along a vast orbit through space. Nothing here is standing still, and that quiet, continuous movement is one of the most reliable clues to how the Milky Way truly works. Once the Milky Way is no longer treated as a unique structure, comparison becomes unavoidable. Galaxies exist across an enormous range of sizes and masses. Some contain only a few million stars. Others hold trillions. Some are bright and orderly, while others are faint, distorted, or barely holding together. The Milky Way sits somewhere in the middle of this spectrum, neither among the smallest nor among the largest, and that position carries quiet significance. At the lower end of the scale are dwarf galaxies. These are small, low-mass systems that orbit larger galaxies or drift independently through space. Many contain only a few billion stars, sometimes far fewer. Some are actively forming stars. Others are ancient and quiet, composed mostly of old, dim stellar populations. Their gravitational grip is weak, and their shapes are easily distorted by interactions with larger neighbours. Dwarf galaxies are not rare. In fact, they are the most common type of galaxy in the universe. The Milky Way itself is surrounded by dozens of them, some visible as faint smudges in the sky, others detectable only through careful surveys. These small companions are not merely background objects. They are evidence of how galaxies grow, merge, and evolve over time. At the opposite extreme are giant galaxies. These systems can be several times larger and more massive than the Milky Way. Some are sprawling spiral galaxies with extended disks. Others are enormous elliptical galaxies, dense and smooth, often found at the centres of galaxy clusters. Their gravity dominates their surroundings, shaping the motion of hundreds or even thousands of nearby galaxies. Between these extremes lies a broad continuum. Galaxy size does not fall into neat categories. There is no single threshold that separates small from large. Instead, galaxies form a distribution shaped by initial conditions, environment, and long histories of interaction. The Milky Way occupies a moderate position within this distribution, large enough to host complex structure, yet small enough to be influenced by neighbours. The most natural comparison is with Andromeda. Andromeda is the nearest large spiral galaxy to the Milky Way, and the only one visible to the naked eye under dark skies. In many ways it is similar. It has spiral arms, a central bulge, a dark matter halo, and a vast population of stars. Yet it is also larger and more massive, with a broader disk and a greater total star count. The two galaxies are bound together by gravity. They are moving toward one another, drawn together over billions of years. This slow approach reveals something important. Neither galaxy exists in isolation. Each is part of a small collection of galaxies known as the local group, a gravitationally bound system containing several dozen members. The local group is modest by cosmic standards. It spans only a few million light-years and contains just a handful of large galaxies. The Milky Way and Andromeda dominate its mass, while smaller galaxies orbit them in complex patterns. There is no central authority here. Gravity governs the group as a whole, with motion shaped by the combined mass of its members. This local environment matters. Galaxies do not grow or evolve independently. Their size and structure are influenced by where they form and what surrounds them. Interactions with nearby galaxies can trigger bursts of star formation, strip gas away, or distort shapes over time. The Milky Way's history includes mergers with smaller galaxies, evidence of which can still be seen in streams of stars arcing through its halo. Comparing galaxies reveals how varied these histories can be. Some galaxies remain relatively isolated, growing slowly and steadily. Others experience frequent interactions, growing rapidly through mergers. Size is not simply a matter of age. It reflects environment, chance, and the complex behavior of matter under gravity. This is why galaxy size follows no simple rule. Larger does not always mean older. Smaller does not always mean simpler. The dwarf galaxy may be ancient, having formed early and changed little since. A massive spiral may be comparatively young, having assembled much of its mass through recent mergers. The universe does not rank galaxies by size in any meaningful hierarchy. Even shape fails as a guide. Spiral galaxies like the Milky Way are often associated with ongoing star formation and ordered rotation. Elliptical galaxies are typically older and more massive, with stars moving in random orbits. Yet these are tendencies, not laws. Exceptions exist at every scale. When placed among its peers, the Milky Way appears ordinary. It is not among the most massive galaxies known. It is not unusually small. It does not occupy a special location. Its properties fall comfortably within the range expected for spiral galaxies in modest groups. This ordinariness is not disappointing, it is informative. It suggests that the processes shaping the Milky Way are common. Star formation, gravitational collapse, mergers, and dark matter halos operate throughout the universe in much the same way. The Milky Way is not a rare outcome. It is a typical expression of cosmic structure, shaped by the same forces that shape countless other galaxies. This realization changes how scale is interpreted. From within, the Milky Way feels immense. Compared to planets and stars, it is. Compared to galaxies across the universe, it becomes one example among many. Its size is significant locally, but not exceptional globally. This shift in perspective does not diminish its complexity. The Milky Way remains a richly structured system with billions of stars, intricate dynamics, and a long history. What changes is its context. It moves from being the largest imaginable structure to being one data point in a much larger population. The question of how common Milky Way-like galaxies are becomes meaningful here. Observations suggest that spiral galaxies of similar size and mass are widespread. They are not the majority, but they are far from rare. The universe appears capable of producing such systems reliably under a range of conditions. The Milky Way's existence does not require fine-tuning or unusual circumstances. That too carries weight. If galaxies like the Milky Way are common, then the processes that made it are fundamental rather than exceptional. Gravity, dark matter, gas dynamics, and time are sufficient. No special ingredients are needed. This perspective also introduces restraint. It becomes clear that size alone does not grant importance. A galaxy's role in the universe is not determined by how many stars it contains or how wide its disk extends. Importance is a human concept. The universe operates without reference to it. Comparing galaxies strips away the illusion of centrality. The Milky Way is not the standard against which all others are measured. It is one member of a vast and varied population. Its size is meaningful but not privileged. Its structure is intricate but not unique. Seen this way, the Milky Way occupies a narrow band between extremes, too large to be simple, too small to dominate, large enough to host complexity, yet modest enough to be shaped by its surroundings. It exists at a scale where structure emerges, but where individuality fades when the view pulls back far enough. That balance is not accidental. It is the natural outcome of cosmic evolution operating across immense time and space. The Milky Way's size, once isolated from context, becomes part of a broader pattern when other galaxies enter the frame, and it is in that comparison that the galaxy begins to shrink, not physically but conceptually, as perspective continues to widen. Beyond the boundaries of the Milky Way, space does not immediately open into emptiness. Instead, it is populated by a small collection of nearby galaxies, bound together by gravity and moving through space as a loose, extended family. This collection is known as the local group, and it defines the immediate cosmic environment in which the Milky Way exists. The local group is not large by universal standards. It spans only a few million light-years and contains a few dozen known galaxies. Most of them are small. Only a handful are large enough to dominate the group's mass and motion. At its heart are two major spirals, the Milky Way and Andromeda, accompanied by a slightly smaller spiral known as the Triangulum Galaxy. Around these larger systems orbit numerous dwarf galaxies, faint and fragile by comparison. Gravity holds this group together. There is no central hub or fixed boundary. The local group is defined by mutual attraction rather than sharp edges. Each galaxy moves in response to the combined gravitational influence of the others, their paths shaped by slow, persistent forces acting over billions of years. The group is not static. It is dynamic, evolving, and quietly active. The Milky Way is not alone within this structure. It is surrounded by satellite galaxies, small companions that orbit within its gravitational influence. Some are visible to the naked eye under ideal conditions. Others are so faint that they were discovered only recently, detected through subtle overdensities of stars rather than direct brightness. These satellites range widely in size, shape, and history. Some are actively forming stars, others are composed almost entirely of ancient stellar populations, their gas long stripped away by interactions with the Milky Way or by internal processes. Their orbits are varied, tilted at different angles, stretching far above and below the galactic disk. Together, they form a complex system of motion around the larger galaxy. These satellites are not permanent. Over time, their orbits decay. Gravitational tides pull at them, distorting their shapes and drawing out long streams of stars. Some are slowly being torn apart, their material absorbed into the Milky Way's halo. Evidence of past mergers can be seen in faint stellar streams arcing through space, remnants of galaxies that no longer exist as distinct objects. This process is ongoing. The Milky Way continues to grow, not by sudden collisions, but by gradual accumulation. Small galaxies fall in, are disrupted, and become part of the larger structure. This is not unique to the Milky Way. It is a common feature of galaxy evolution throughout the universe. The same dynamic applies across the local group. Andromeda has its own system of satellite galaxies, some of which show signs of similar tidal disruption. The two major spirals dominate the group's mass, and their gravitational interaction shapes the motion of everything around them. Smaller galaxies orbit one or the other, or move along more complex paths influenced by both. The local group itself is not isolated. It exists within a broader cosmic environment, influenced by nearby groups and larger structures. Gravity extends outward indefinitely, weakening with distance but never truly ending. The local group's boundaries are therefore not fixed. They are regions where its gravitational influence fades into that of the surrounding universe. This makes the concept of membership slightly ambiguous. Some galaxies lie at the edges of the group, their motions influenced by both the local group and external structures. Determining whether they belong is a matter of careful measurement and interpretation. Even here, uncertainty remains, not because of error, but because nature rarely draws clean lines. Despite this complexity, the local group remains small. On cosmic scales, it is a modest gathering. It contains only a tiny fraction of the galaxies in the observable universe. Vast clusters elsewhere contain hundreds or thousands of galaxies packed into dense regions. Compared to those environments, the local group is sparse and quiet. This relative calm has consequences. Galaxies in dense clusters experience frequent interactions, rapid mergers, and intense gravitational effects. The local group, by contrast, evolves slowly. Encounters are rare and unfold over immense spans of time. Changes occur, but they are measured in billions of years rather than millions. The motion within the group reflects this pace. Galaxies drift along curved paths, responding to gravity with patience rather than urgency. Speeds are significant, but distances are vast. Nothing happens quickly. Even the eventual interaction between the Milky Way and Andromeda, inevitable under current understanding, unfolds on timescales that dwarf human history. This slow motion offers insight. By studying the local group, astronomers gain a laboratory for understanding galaxy evolution in a low-density environment. The interactions are close enough to observe in detail, yet gentle enough to preserve evidence of past events. The group retains memory in the form of stellar streams, orbital patterns, and subtle distortions. These observations reveal a deeper truth. Galaxies are not solitary objects drifting independently through space. They exist in communities shaped by long-term relationships with their neighbours. The Milky Way's structure, star formation history, and outer halo all bear the marks of these interactions. At the same time, the local group's limited scale is striking. It is easy to imagine the Milky Way as part of a vast galactic empire surrounded by countless large companions. The reality is more restrained. There are only a few major players nearby. Beyond them lies a great emptiness before the next significant structures appear. This emptiness matters. It defines the Milky Way's immediate context. The galaxy's motion, growth, and future are shaped primarily by this small collection of neighbours. On larger scales, other forces come into play, but locally, the local group sets the stage. Understanding this neighbourhood reframes the Milky Way's place in the universe. The galaxy is not at the centre of a grand arrangement. It is one member of a modest group bound by gravity, moving through space alongside familiar companions. Its size, once impressive in isolation, becomes just one factor among many. The local group is both intimate and humbling. Intimate because it is the closest cosmic structure beyond the Milky Way itself, containing galaxies that can be studied in detail. Humbling because it is so small compared to the vast architecture of the universe beyond. This contrast sharpens perspective. The Milky Way dominates its immediate surroundings, yet those surroundings are limited. The local group is a small island in a much larger cosmic ocean. Its scale is significant locally, but negligible when the view continues to widen. In this way, the local group marks a transition. It is the point where the Milky Way stops being the largest structure in view and becomes part of something slightly bigger. Not yet lost in the vastness of clusters and superclusters, but no longer alone. It is a reminder that cosmic belonging is layered. Galaxies belong to groups, groups belong to larger structures. Each level adds context, and each step outward reduces the significance of the previous one. The local group is one such step, modest in size, yet crucial for understanding how the Milky Way fits into the wider universe. And even here, in this small and familiar neighbourhood, gravity continues its slow work, quietly reshaping the future without haste or spectacle. Beyond small groups of galaxies, gravity begins to organise matter on a far larger scale. Individual galaxies are not scattered randomly through space. They gather. Where gravity has had time to work, galaxies fall together into dense regions known as galaxy clusters. These clusters are among the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies moving together through space. A galaxy cluster is not simply a crowded patch of galaxies, it is a deep gravitational well. The combined mass of its galaxies, hot gas and dark matter, binds the entire system together. Galaxies orbit a shared center of mass. Hot plasma fills the space between them, glowing faintly in X-rays. Dark matter dominates the total mass, shaping the cluster's structure while remaining invisible. Clusters are defined by this binding. If galaxies are moving fast enough to escape, they are not part of the cluster. Membership is determined not by appearance, but by motion and gravity. In this sense, clusters are genuine physical objects, not just visual groupings. The nearest large example is the Virgo cluster. It lies tens of millions of light-years away and contains well over 1,000 galaxies. Some are massive spirals. Many more are elliptical or irregular systems shaped by repeated interactions. The Virgo cluster is not symmetrical or orderly. It is still forming, still pulling galaxies inward, still evolving. The Milky Way does not belong to this cluster. Instead, it sits on the outskirts, moving through a quieter region of space. Yet the Virgo cluster still matters. Its immense mass influences the motion of galaxies far beyond its visible core. Even at great distances, its gravitational pull subtly shapes the paths of smaller groups. This influence reveals an important shift in scale. Within the local group, gravity feels personal. Individual galaxies matter. Within a cluster, the identity of any single galaxy becomes less important. What matters is the total mass and how it is distributed. The view begins to change from individual structures to collective behavior. Clusters themselves do not exist in isolation. They're often connected to other clusters through long, faint filaments of galaxies and dark matter. These connections form even larger arrangements known as superclusters. A supercluster is not a tightly bound object in the same way a cluster is. It is a vast region where clusters and groups are drawn together along large-scale structures in the universe. Superclusters stretch intuition even further. They span hundreds of millions of light-years. Their shapes are irregular, web-like, and diffuse. Gravity still plays a role, but expansion of the universe competes with attraction on these scales. Some regions within a supercluster may eventually collapse further. Others may slowly drift apart. One such structure contains the Virgo cluster, along with many other clusters and groups. The Milky Way, through the local group, belongs to this larger arrangement. From this perspective, the galaxy's address becomes layered. It exists within a group which lies near a cluster, which itself is part of a supercluster, spanning an enormous volume of space. At each step outward, scale changes meaning. Distances that once felt vast become small relative to what surrounds them. The local group, which seemed expansive when viewed alone, becomes a minor feature at the edge of a much larger structure. The Milky Way's size, once overwhelming, fades into context. This progression is not just conceptual, it is observable. Large galaxy surveys map the positions of millions of galaxies, revealing patterns that resemble a cosmic web. Dense nodes mark clusters, filaments connect them, vast voids stretch between, regions with very few galaxies at all. Matter in the universe is not evenly distributed. It organizes itself into structure on every scale. Clusters sit at the nodes of this web. They are crossroads where filaments intersect, where matter has flowed over billions of years. Their mass grows through steady accretion, pulling in galaxies from surrounding regions. The Virgo cluster is one such node, a focal point in its local cosmic environment. This environment shapes the galaxies within it. Galaxies in clusters behave differently from those in quieter regions. Gas can be stripped away as galaxies move through hot intracluster plasma. Star formation can be quenched. Shapes can be altered through repeated gravitational encounters. Life inside a cluster is crowded and turbulent on cosmic timescales. The Milky Way's quieter setting stands in contrast. It has avoided the intense environment of a dense cluster, allowing it to retain its gas and continue forming stars over long periods. This difference in surroundings has influenced its evolution, not through dramatic events, but through the absence of them. Scale continues to expand beyond clusters and superclusters. Even the largest of these structures are only part of a broader pattern. On the very largest scales, the universe appears statistically uniform. No direction is favoured. No region is truly central. Structures repeat, but none dominates the whole. This is where intuition finally gives up. Superclusters are so large that they cannot be easily pictured as objects. Their boundaries are fuzzy. Their futures are uncertain. Some may remain loosely connected forever. Others may eventually fragment as cosmic expansion pulls them apart. The universe does not insist on neat endings. Measurements become less certain here. Distances are harder to define. Motions are slower relative to the scale involved. Gravity competes with expansion in ways that are still being refined by observation and theory. The largest structures known are also the least well understood, and yet the pattern remains clear. From stars to galaxies, from galaxies to groups, from groups to clusters, and from clusters to superclusters, matter organizes itself hierarchically. Each level emerges from the same fundamental forces, operating over larger distances and longer times. The Milky Way's place within this hierarchy is not special. It does not sit at the center of a cluster. It does not anchor a supercluster. It occupies a modest position on the outskirts of a larger structure, one thread in a much wider web. Its significance shrinks with every widening of perspective. This shrinking is not physical. The galaxy does not become smaller. Its stars do not disappear. What changes is context. The scale against which it is measured grows, and familiar reference points lose their authority. There is something quietly disorienting about this. Each step outward removes another layer of importance. The Milky Way is no longer the largest structure. The local group is no longer exceptional. Even clusters become just nodes in a pattern that extends far beyond them. And still, the universe continues. Beyond superclusters lie structures that are no longer bound in any meaningful sense. Expansion dominates. Distances grow. Regions drift apart, never to interact again. The idea of neighborhood itself begins to break down. Clusters and superclusters mark the last places where gravity still clearly organizes matter on the largest scales. They are the final echoes of structure before uniformity takes over. Beyond them, the universe smooths out, and scale becomes something that can only be described statistically rather than experienced. From this vantage point, the Milky Way feels small in a new way, not insignificant but contextualized. It is part of a chain of belonging that stretches outward through increasingly vast arrangements, each one reducing the apparent importance of the previous. The widening does not stop here, but by the time clusters and superclusters enter the picture, the mind has already crossed a threshold. Scale has moved beyond intuition and into abstraction. Structures are no longer grasped as objects, but as patterns. And in those patterns, the Milky Way becomes what it truly is. One galaxy among many, moving quietly through a universe that is far larger, far less personal, and far more extensive than it first appeared. On the largest scales that can be observed, the universe does not look random. Galaxies are not sprinkled evenly through space like grains of dust. They gather into patterns that repeat across enormous distances, forming a structure so vast that individual galaxies disappear into it. This arrangement is known as the large-scale structure of the universe, and it reshapes how size and place are understood. At this scale, the universe resembles a network. Matter collects along long thin strands called filaments. These filaments intersect at dense regions known as nodes, where galaxy clusters are found. Between them lie vast voids, enormous regions of space containing very few galaxies at all. The result is a structure often described as a cosmic web, stretching across hundreds of millions of light years. This pattern is not aesthetic or metaphorical. It is a physical consequence of how matter evolved after the early universe. Small fluctuations in density, present shortly after the universe became transparent to light, were amplified by gravity over billions of years. Regions slightly denser than average pulled in more matter. Regions slightly emptier lost material to their surroundings. Over time, these differences grew into the web-like structure seen today. The evidence for this pattern comes from observation, not assumption. Large galaxy surveys have mapped the positions of millions of galaxies across the sky, revealing this structure directly. One of the most influential efforts, the Sloan Digital Sky Survey, charted the three-dimensional distribution of galaxies over vast volumes of space. Its results showed unmistakable filaments and voids, confirming predictions that had existed only in simulations before. What emerges from these maps is scale beyond familiarity. Individual galaxies vanish into dots. Groups and clusters become knots along filaments. Voids stretch across distances so large that light itself takes hundreds of millions of years to cross them. The universe begins to look less like a collection of objects and more like a pattern governed by statistical behavior. This raises a natural question. Why does matter arrange itself this way at all? Why not spread out smoothly, filling space evenly in every direction? The answer lies in gravity and time. In the early universe, matter was distributed almost uniformly, but not perfectly. Tiny variations in density existed at the level of one part in many thousands. Gravity acted relentlessly on these differences. Where matter was slightly denser, gravity pulled more material inward. Where it was slightly thinner, matter flowed away. Over billions of years, these small imbalances grew into vast structures. Dark matter plays a central role in this process. Unlike ordinary matter, dark matter does not interact with light or pressure. It began clumping early, forming the scaffolding of the cosmic web. Ordinary matter fell into these gravitational wells later, forming stars and galaxies along the same underlying framework. The visible universe traces a structure built largely by something that cannot be seen. This is why filaments exist. They are regions where dark matter density is higher, guiding the flow of gas and galaxies along preferred paths. Nodes form where filaments intersect, creating deep gravitational wells that grow into galaxy clusters. Voids form where matter has been drained away, leaving behind immense expanses of near emptiness. Nothing about this structure is designed. It is an emergent outcome of simple physical laws applied over extraordinary spans of time. Gravity amplifies small differences. Expansion stretches everything outward. Together, they produce order without intention. From within a galaxy, this structure is impossible to sense. The Milky Way feels isolated. Its neighbouring galaxies form a modest group. Beyond that lies apparent emptiness. But this impression is misleading. The galaxy sits within a filament of the cosmic web. one thread among countless others. That filament connects the local group to larger structures far beyond immediate perception. In this context, the Milky Way becomes a single point, not metaphorically, but practically. Its diameter, vast by human standards, is negligible compared to the thickness of a filament or the size of a void. The entire local group occupies a region so small relative to the web that it disappears into a dot on cosmological maps. This is where scale takes on a different meaning. Distances are no longer grasped through analogy. They are understood statistically. The universe becomes something described by distributions rather than landmarks. Concepts like average density and correlation length replace familiar notions of neighborhood and proximity. Even clusters once considered enormous shrink in significance. They become bright knots along filaments, impressive locally but unremarkable in the overall pattern. The cosmic web does not center on any one cluster or supercluster. It extends in all directions, repeating without preference. This lack of centrality is important. No location in the universe occupies a privileged position within the web. The pattern looks statistically similar no matter where it is observed, provided the scale is large enough. This principle, known as the cosmological principle, is supported by extensive observation. The universe has structure, but no center. At the same time, the web is not infinite in its complexity. On the very largest scales, beyond those of filaments and voids, the universe smooths out. Matter becomes evenly distributed again when averaged over sufficiently large volumes. Structure exists, but it does not continue indefinitely to larger and larger scales. This boundary is subtle. It is not marked by an edge or a visible transition. It is identified through analysis, by measuring how density variations change with scale. Beyond a certain point, adding more volume does not reveal new structure, only repetition. Here, uncertainty reappears. The exact scale at which the universe becomes fully uniform is still refined through observation. Measurements depend on survey depth, observational limits, and assumptions about unseen matter. The largest structures known may not be the largest that exist within the observable universe. Even so, the picture is clear enough to be unsettling. The Milky Way is not embedded in a simple hierarchy of ever larger objects. It is embedded in a pattern, a web shaped by forces acting long before the galaxy formed, and on scales that dwarf it entirely. From this vantage point, familiar measures of size lose their emotional weight. A galaxy, tens of thousands of light years across, feels large only until it is placed against filaments, hundreds of millions of light years long. The intuition that once struggled with galactic scale now fails completely. This failure is not a weakness. It marks the boundary between human experience and cosmic reality. The universe does not arrange itself in ways that are easy to imagine. It arranges itself according to physics, indifferent to comprehension. And yet, the structure can be known. Not felt, not pictured in full, but understood through careful measurement and theory. The cosmic web is one of the most robust discoveries of modern cosmology, supported by independent observations across different wavelengths and techniques. Within that web, the Milky Way remains exactly what it always was, a spiral galaxy filled with stars, gas, dust, and dark matter. Its internal complexity does not vanish. Its history does not become less real. What changes is scale. The galaxy's importance collapses relative to the structure surrounding it. It becomes one luminous point among billions, threaded into a pattern too large to notice any individual contribution. The web does not care where one galaxy sits. It cares only about mass and gravity acting across vast distances. This realization carries a quiet finality. The question of how big the Milky Way is has now been overtaken by a larger one. Not how large a single galaxy can be, but how small any one galaxy becomes when placed inside the full architecture of the universe. The cosmic web does not erase the Milky Way. It simply absorbs it into something far larger, where scale is no longer personal, and where even galaxies lose their individuality when the view pulls back far enough. There is a point where size stops feeling meaningful. It does not arrive suddenly. It emerges gradually as perspective continues to widen, carrying familiar structures farther and farther from the center of attention. What once felt enormous begins to shrink, not physically, but conceptually. Scale changes what matters. At galactic distances, the Milky Way feels vast. Its diameter spans tens of thousands of light years. Its star count overwhelms intuition. Its structure is complex enough to demand careful study. From nearby, it commands attention. From farther away, something changes. As distance increases, detail fades. Spiral arms blur. Individual stars disappear. The galaxy becomes a luminous patch, then a smudge, then a point. Nothing about the Milky Way itself has altered. Only the scale of observation has shifted. This shift is fundamental to cosmology. Cosmology does not study individual objects in isolation. It studies populations, patterns, distributions. At large enough scales, the universe is not described in terms of particular galaxies, but in terms of averages, densities, and statistical relationships. Individual identity gives way to collective behavior. This is not philosophical abstraction. It is practical necessity. The observable universe contains hundreds of billions of galaxies. No theory could track them one by one. Instead, cosmology treats galaxies as traces of matter, markers that reveal how mass is arranged across space. What matters is not which galaxy is where, but how galaxies are distributed overall. This is where significance begins to dissolve. At small scales, galaxies are distinct. Each has its own shape, history, and internal dynamics. At larger scales, those differences blur into noise. A spiral galaxy and an elliptical galaxy contribute similarly to measurements of large-scale structure. Their individuality becomes irrelevant to the questions being asked. This transition is not arbitrary. It occurs because gravity, expansion, and time operate differently depending on scale. On the scale of galaxies, internal structure matters. On the scale of clusters, mass dominates. On the scale of the cosmic web, only the statistical distribution of matter remains. Cosmology formalizes this shift through statistical tools. Rather than asking where a particular galaxy is, cosmologists ask how likely it is to find a galaxy at a given distance from another. They measure correlation functions, power spectra, and average densities. These quantities describe the universe without reference to any specific object. In this framework, galaxies become interchangeable. One luminous point can stand in for another. What matters is that they trace the underlying distribution of matter. Individual names, shapes, and histories fall away. The universe becomes something described by smooth curves and probability distributions rather than by landmarks. This can feel unsettling. The Milky Way, once central to understanding, now appears as just one sample among billions. Its unique features no longer matter to the largest questions. It does not define the universe's structure. It merely participates in it. Yet this reduction is not dismissive. It is precise. By stripping away individuality, cosmology reveals patterns that would otherwise remain hidden. The large-scale uniformity of the universe, the presence of filaments and voids, and the influence of dark matter all emerge more clearly when galaxies are treated statistically. There is also a deeper reason why galaxies lose significance with distance. Light itself imposes limits. The farther away a galaxy is, the less information its light carries. Details are lost to distance, redshift, and cosmic expansion. At extreme distances, galaxies appear not as complex systems, but as faint fluctuations against the background. Beyond a certain point, even those fluctuations fade. The earliest light in the observable universe does not come from galaxies at all, but from a time before stars existed. At that scale, galaxies have not merely lost importance, they have not yet formed. The universe's structure is encoded instead in subtle variations in radiation, long before individual objects emerge. This places galaxies in a narrow window of relevance. They matter enormously on human and galactic scales. They matter less on the largest cosmological scales. Their significance peaks and then declines as perspective expands. The Milky Way follows this pattern precisely. Up close, it is a dominant structure. It shapes everything familiar. From farther away, it becomes one galaxy among many. From even farther, it becomes a data point. A single entry in a catalogue contributing to averages and distributions without standing out. This is not because the Milky Way is small, it is because the universe is large. Scale changes meaning. It changes which questions can be asked and which details matter. When studying galaxy formation, individuality is essential. When studying the expansion of the universe, individuality becomes distraction. This layered relevance is one of cosmology's quiet lessons. Nothing is always important. No structure retains significance at every scale. Importance depends on context, and context depends on distance. This does not imply that galaxies are unimportant in any absolute sense. It implies that significance is scale-dependent. The Milky Way remains essential to understanding stellar evolution, planetary systems, and the conditions that allow observers to exist at all. It becomes irrelevant only when questions shift beyond its scale. Cosmology accepts this without discomfort. It does not privilege familiarity. It does not preserve meaning where it no longer applies. It allows structures to fade when they no longer influence the phenomena under study. This approach reveals something subtle. The universe does not organize itself around objects. It organizes itself around laws. Objects emerge where conditions allow them, persist for a time, and then lose relevance as scale changes. From this vantage point, the Milky Way's reduction to a data point is not a diminishment. It is a clarification. The galaxy does not disappear. It simply stops being the right unit of description. The universe becomes smoother, simpler, and more uniform as distance increases, not because structure vanishes, but because structure averages out. This averaging is not complete. Even at the larger scales, subtle patterns remain. Density variations persist. Expansion is not perfectly uniform in every direction, but the identity of individual galaxies no longer enters the picture. The mind resists this transition. It prefers concrete objects to statistics. It prefers named structures to abstract distributions. Yet the universe does not accommodate preference. It reveals itself differently depending on how far the view extends. There is a quiet humility in this. The Milky Way, once the largest imaginable structure, becomes small without ever shrinking. Its stars continue to burn. Its planets continue to orbit. Its internal history remains rich and complex. Only its relevance to certain questions changes. This distinction matters. Small does not mean trivial. Insignificant does not mean uninteresting. It simply means that a different scale now governs understanding. When galaxies become small, it is not because they fail to matter. It is because the universe has grown larger than they are. There is a natural temptation to imagine the universe as something that can be fully seen, if only the instruments were powerful enough. That temptation is understandable. Telescopes peer deeper each decade. Surveys map ever larger volumes of space. The visible horizon expands as technology improves. It can feel as though the universe is gradually revealing itself in full. But there is a hard limit built into reality itself. The observable universe is not defined by the reach of telescopes, nor by the ambition of observation. It is defined by time and by the finite speed at which information can travel. Light does not arrive instantly. It moves through space at a fixed speed, and the universe has existed for only a finite duration. As a result, there are regions whose light has simply not had time to reach Earth. The observable universe is the portion of the cosmos from which light has reached us since the beginning of cosmic expansion. Anything beyond that boundary is not hidden by dust or distance in the ordinary sense. It is hidden by time. No signal from those regions has ever arrived. No image can be formed, no measurement taken, no observation made, regardless of future technology. This boundary is known as the cosmic horizon. It is not a physical wall. It does not mark the edge of existence. It marks the edge of causal contact. Beyond it, events may be occurring, galaxies may be forming, and structures may be evolving, but they are forever disconnected from observation from Earth. The reason for this lies in the nature of light and cosmic history. The universe has been expanding for roughly 13.8 billion years. Light emitted shortly after the universe became transparent has been travelling ever since. But during that journey, space itself has expanded, stretching the distances between objects. As a result, the most distant regions we can observe today are much farther away than 13.8 billion light-years. This leads to a counterintuitive result. The observable universe has a radius of roughly 46 billion light-years, not because light has travelled faster than expected, but because the space it travelled through expanded while the light was en route. Distance and time are entwined in ways that intuition does not easily accommodate. The cosmic horizon is therefore dynamic. As time passes, light from more distant regions has time to arrive, and the observable universe grows larger. But this growth does not mean the universe itself is expanding into something else. Space itself is stretching everywhere, carrying galaxies away from one another in all directions. There's also another horizon to consider. Because expansion is accelerating, driven by dark energy, there are regions whose light will never reach us, no matter how long the universe exists. They are receding faster than light can traverse the expanding space between us and them. These regions are permanently beyond contact. This introduces a quieter symmetry. The observable universe is not the same as the universe itself. It is a subset, defined by physical limits rather than by boundaries of existence. There is no reason to think that the universe ends at the cosmic horizon. In fact, all evidence suggests the opposite. The universe almost certainly extends far beyond what can be observed. Observations of large-scale uniformity show that the universe looks statistically similar in every direction. There is no sign of curvature or edge within the observable region. When the same patterns repeat across vast distances, the simplest explanation is that those patterns continue beyond the horizon as well. Cosmological models based on general relativity support this view. They allow for a universe that is finite but unbounded, or infinite outright. Current measurements cannot distinguish between these possibilities conclusively. What is clear is that the observable universe is not the whole story. It is the portion accessible to observation, not the entirety of what exists. This distinction matters. When people speak about the size of the universe, they often mean the size of the observable universe. This is understandable, but incomplete. The universe itself may be vastly larger, perhaps infinitely larger, than the region that can ever be seen. Here, uncertainty becomes unavoidable. There is no observational method that can probe beyond the cosmic horizon. No experiment can retrieve information from regions causally disconnected from us. Questions about what lies beyond are constrained by physics itself. They are not unanswered because of insufficient effort, but because of fundamental limits. This is where mystery enters legitimately, not as speculation, not as guesswork, but as acknowledged absence of information. Science does not fill this gap with invention. It names the boundary and stops. Within the observable universe, scale becomes extreme. There are hundreds of billions of galaxies, each containing billions or trillions of stars. Vast filaments stretch across hundreds of millions of light years. Enormous voids span comparable distances. The largest structures fill significant fractions of the observable volume. Against this backdrop, the Milky Way becomes almost vanishingly small. Its diameter, once measured in tens of thousands of light years, is negligible compared to the size of the observable universe. If the observable universe were scaled down to the size of Earth, the Milky Way would be smaller than a single cell. Even this comparison struggles to convey the imbalance. The Milky Way occupies a volume so tiny relative to the whole that it effectively disappears in cosmological calculations. It does not influence the universe's expansion. It does not affect large-scale geometry. It does not register except as one of countless traces of matter, and yet it remains where everything familiar happens. This is another quiet paradox of scale. The Milky Way is insignificant to the structure of the observable universe, yet absolutely central to every human experience that has ever occurred. Both statements are true, depending on perspective. The observable universe does not privilege location. There is no center within it. Every observer sees themselves at the center of their own observable sphere, not because they occupy a special position, but because light arrives equally from all directions. Any observer anywhere in the universe would make the same observation. This reinforces a deeper principle. The laws of physics do not change with position. The universe does not organize itself around particular galaxies or observers. Structure exists, but meaning does not propagate outward from any one point. The observable universe is therefore not a container with contents arranged around a focus. It is a sphere defined by information limits, centered on the observer only by circumstance. Beyond it, the universe continues without reference to that observer at all. This understanding reframes the question of size. Asking how big the universe is becomes less meaningful than asking what portion of it can ever be known. The answer to that question is finite, measurable, and constrained. Everything beyond that remains real but inaccessible. This boundary does not shrink discovery. Within the observable universe, there is more complexity, structure, and history than any single mind can absorb. The limitation is not lack of material, but abundance beyond capacity. Still, the existence of an unseen beyond carries weight. It implies that even the most comprehensive maps will always be partial, that knowledge will always be local in a cosmic sense, that the universe is larger than its description. In this context, the Milky Way's scale takes on a final form. It is vast relative to human intuition, modest relative to galaxies as a whole, insignificant relative to the observable universe, and almost meaningless relative to whatever lies beyond the cosmic horizon. This cascade of diminishing relevance is not bleak, it is clarifying. The universe does not ask to be grasped all at once. It reveals itself in layers, each one bounded by physical limits. The observable universe is one such layer, defined not by imagination, but by light, time, and expansion. Beyond it, the universe continues silently, unconcerned with observation. And within it, the Milky Way drifts on, a small luminous structure inside a vast region that itself may be only a fraction of everything that exists. At first glance, the universe appears static. The stars hold their patterns, galaxies seem fixed against the sky. On human timescales, nothing obvious shifts. For centuries, this apparent stillness shaped how the cosmos was understood. The universe was assumed to be eternal and unchanging, a vast but stable backdrop in which events unfolded. That assumption did not survive careful measurement. In the early 20th century, astronomers began to notice something subtle but consistent. Light from distant galaxies was shifted toward longer wavelengths. This shift, known as redshift, suggested that those galaxies were moving away. More distant galaxies showed larger shifts. The pattern was not random. It followed a rule. The discovery was transformative. Working with observations of distant galaxies, Edwin Hubble demonstrated that the universe is expanding. Galaxies are not simply moving through space. Space itself is stretching, carrying galaxies along with it. The farther away a galaxy is, the faster it recedes. This relationship is now fundamental to cosmology. Recession speed increases with distance. Nearby galaxies drift slowly. Distant ones pull away rapidly. At the larger scale, some regions are receding so quickly that their light will never reach Earth. Expansion is not a local phenomenon. It is a property of the universe as a whole. This realization immediately reshaped ideas of size. If the universe is expanding, then distances are not fixed. The scale of everything changes with time. The universe was smaller in the past and will be larger in the future. Size becomes a moving target rather than a static measure. This undermines a deeply rooted intuition. In everyday experience, size is stable. A mountain does not grow because time passes. A distance remains the same once measured. Cosmic expansion breaks that expectation. Distances between galaxies increase continuously, even though the galaxies themselves remain intact. The Milky Way is unaffected internally by this expansion. Gravity binds its stars tightly enough that the galaxy does not stretch with the universe. Neither do planetary systems or atoms. Expansion becomes noticeable only on scales where gravity is weak compared to the overall expansion of space. This distinction matters. It explains why the Milky Way can feel stable and complete while existing within an expanding universe. Locally, gravity dominates. Globally, expansion prevails. Both are true at once. Expansion also eliminates the idea of a cosmic center. If every distant galaxy is receding, then every location appears central from its own perspective. An observer in another galaxy would see the same pattern, with galaxies moving away in all directions. There is no preferred position, no central point from which expansion originates. This is not a limitation of observation. It is a property of the universe. Expansion does not occur outward from a single location. It happens everywhere at once. Space expands uniformly on large scales, carrying galaxies apart without reference to a center. This challenges everyday language. Phrases like expanding into space are misleading. The universe is not expanding into anything. Space itself is expanding, and it does so uniformly. Asking where the center is becomes meaningless, because no such location exists. This realization reframes perspective completely. The Milky Way does not sit near a center. It does not occupy a special position. Its location is ordinary, not because it lies far from a center, but because there is no center to be far from. Expansion also alters how distance is interpreted. Light from distant galaxies began its journey when the universe was much smaller. By the time it arrives, the space it traveled through has expanded significantly. This means that the distance to a galaxy depends on when it is measured. Distance becomes time-dependent. As a result, statements about how far away something is require context. Is the distance being described as it was when the light was emitted, as it is now, or as it will be in the future? Each answer is correct in its own frame. None aligns cleanly with intuition. This complexity grows with scale. At modest distances, the effects are small. At cosmological distances, they dominate. The observable universe appears larger than its age alone would suggest, because space expanded while light was in transit. Expansion also introduces horizons. Some galaxies recede so quickly that their light can no longer reach Earth. They cross a boundary beyond which communication becomes impossible. Not because light is too slow in a static sense, but because space itself expands faster than light can traverse. This creates a universe with limits built into its structure. Not all of existence is accessible. Not all regions can influence one another. Expansion sets boundaries that no technology can overcome. Within these boundaries, scale continues to stretch. Structures that once seemed large shrink in relative importance as the universe grows. The Milky Way's size becomes negligible compared to the distances between galaxy clusters. Even clusters become small compared to the full observable volume. Expansion accelerates this effect. As time passes, distant galaxies move farther away. Their light becomes more redshifted. Eventually, many will fade from view entirely. The universe becomes emptier from any given vantage point, not because matter disappears, but because expansion carries it beyond observational reach. This future is already encoded in the present. The pattern of recession observed today implies a universe that grows ever larger and more diffuse. Local structures remain bound. Everything else drifts apart. Seen through this lens, size becomes contextual rather than absolute. The Milky Way is large relative to stars, small relative to galaxies as a population, insignificant relative to the expanding universe as a whole. Each statement is accurate within its own frame. Expansion forces a final adjustment of perspective. The universe is not a static container filled with objects of fixed size. It is a dynamic system in which scale itself evolves. Distances stretch, horizons shift. What can be seen changes with time. This does not diminish understanding, it deepens it. Expansion reveals that size is not just a property of objects, but a relationship shaped by time, motion, and geometry. The universe does not offer a single scale at which everything makes sense. It requires many. The Milky Way drifts within this expanding space, unchanged internally, yet increasingly isolated from distant regions. Its lack of centrality is not a loss. It is a consequence of uniformity. Every galaxy shares this condition. None is central, none is privileged. All occupy positions that are locally meaningful and globally unremarkable. Expansion removes the final illusion of placement. There is no cosmic middle, no outer edge toward which everything moves, only space stretching everywhere, carrying galaxies along paths that look the same from any vantage point. In this expanding universe, perspective becomes the only anchor. And from that perspective, the Milky Way is exactly where it should be. Not at the center, not at the edge, just somewhere inside a universe that continues to grow, indifferent to position, and vast beyond any fixed measure of size. As the view continues to widen, a quiet idea settles into place. The universe, when seen on its larger scales, does not favour any particular location. No region stands out as central. No direction appears preferred. The cosmos looks much the same no matter where the observation is made, provided the scale is large enough. This idea is known as the cosmological principle, and it underpins modern cosmology. Stated simply, the cosmological principle holds that the universe is homogeneous and isotropic on large scales. Homogeneous means that, averaged over vast distances, matter is distributed evenly. Isotropic means that the universe looks the same in every direction. These statements are not claims about local detail. They do not deny the existence of galaxies, clusters, filaments, or voids. They describe what remains after those details are averaged away. This distinction is crucial. Up close, the universe is highly structured. Galaxies cluster. Matter flows along filaments. Voids stretch across enormous regions. But when these structures are viewed collectively, over distances far larger than any single feature, the differences balance out. No location emerges as special. This conclusion did not arise from philosophical preference. It emerged from observation. Large galaxy surveys show that while structure exists, its statistical properties are remarkably consistent across the observable universe. Measurements of the cosmic microwave background radiation reinforce this picture, revealing a universe that is extraordinarily uniform when examined on the larger scales. Uniform does not mean simple. The universe is not empty or featureless. It is complex and dynamic. Uniformity here refers to averages, not appearances. It means that any sufficiently large region resembles any other when measured by the same criteria. This has an unsettling implication. If the universe looks the same everywhere, then there is no natural centre. The Milky Way does not occupy a privileged position. Neither does the local group, nor the Virgo cluster, nor any other structure. Every galaxy, from its own perspective, appears to sit near the centre of its observable universe. This symmetry is not an illusion. It follows directly from cosmic expansion and the uniform distribution of matter. Because space expands uniformly, observers in different locations see the same large-scale behaviour. Recession appears isotropic from every vantage point. No observer can claim a special seat. The idea of cosmic privilege quietly dissolves here. For much of history, it was assumed that the universe must be organised around something important. Earth once filled that role. Later, the Sun. Later still, the Milky Way. Each step outward removed a layer of centrality. The cosmological principle completes that process. Nothing occupies the middle. This does not mean the universe lacks structure or meaning. It means that meaning does not arise from position. Location carries no inherent significance on cosmic scales. The laws of physics operate the same way everywhere that can be observed. This sameness can provoke mixed reactions. On one hand, it strips away comfort. There is no favoured place, no cosmic spotlight. The Milky Way becomes one ordinary galaxy among billions, its position unremarkable, despite its internal richness. On the other hand, it introduces a different kind of coherence. A universe governed by the same rules everywhere is a universe that can be understood. Uniformity allows patterns to be identified, laws to be tested, and predictions to be made. Without it, cosmology would collapse into parochial description. The emotional tension here is subtle. Being ordinary can feel diminishing when framed through human intuition. The word suggests insignificance, a loss of uniqueness. But in cosmology, ordinariness carries a different meaning. It means representative, typical, governed by the same processes that operate everywhere else. The Milky Way exemplifies this. It is not the largest galaxy. It is not the smallest. It is not unusually active or unusually quiet. Its mass, structure, and star formation history fall well within the expected range for spiral galaxies in modest environments. Nothing about it requires exceptional explanation, and yet its internal complexity remains staggering. Hundreds of billions of stars orbit within it. Planetary systems form and evolve. Chemical elements forged in stellar interiors cycle through generations of stars. Complexity thrives locally even as global sameness holds. This coexistence is not a contradiction. The cosmological principle does not deny local richness. It allows it. Uniformity emerges only when enough volume is considered. Below that scale, diversity flourishes. Above it, differences fade. This layered reality is one of the universe's defining features. Zoom in and detail explodes. Zoom out and patterns simplify. Neither view is more correct than the other. They answer different questions. Cosmology is concerned with the widest view. At that scale, individuality fades by necessity. Galaxies are no longer characters in a story. They are samples in a distribution. Their specific histories matter less than their collective behavior. This does not erase the Milky Way story. It simply places it within a much larger context. The galaxy's lack of special status does not negate its role as a home, a laboratory, or a source of wonder. It clarifies that these roles are local, not universal. There is a quiet honesty in this framing. The universe does not appear arranged for observation. It does not elevate certain locations or structures. It unfolds according to simple principles applied everywhere, producing complexity where conditions allow it, and sameness when viewed broadly enough. The absence of privilege is itself informative. It suggests that the processes shaping the Milky Way are not rare accidents. They are common outcomes. Given similar conditions elsewhere, similar structures emerge. The galaxy's existence does not require special pleading. This has implications beyond astronomy. It challenges the instinct to place meaning at the center of scale. Importance does not increase with size. Centrality does not confer value. The universe operates independently of such measures. The Milky Way's ordinariness, then, is not a loss. It is a confirmation. It confirms that the laws observed locally are universal, that the night sky above Earth is governed by the same physics that shapes galaxies across the observable universe. This realization can feel both humbling and stabilizing. Humbling because it removes the last traces of cosmic favoritism. Stabilizing because it grounds understanding in consistency rather than exception. The universe is vast without being hierarchical. It does not build toward a center or peak. It spreads outward uniformly, generating structure without ranking it. Galaxies form where matter accumulates. Groups and clusters emerge where gravity draws them together. None are designated as more important than the rest. From this vantage point, vastness becomes impersonal. Scale no longer implies dominance. Size no longer implies significance. The larger structures are not more meaningful than smaller ones. They simply operate under different regimes. The Milky Way remains what it has always been. A spiral galaxy of moderate size, rich in stars and history, moving through space according to the same principles that govern everything else. Its lack of privilege does not diminish its reality. It situates it properly. In a universe that looks much the same from everywhere, no galaxy is special by position alone, and that sameness, far from emptying the cosmos of meaning, reveals a deeper order, one where complexity arises locally, uniformity emerges globally, and perspective determines which truth comes into focus. Vastness in this sense does not grant status, it removes it. What remains is a universe that is coherent, consistent, and indifferent to placement, offering no centre to stand upon, yet allowing understanding to grow wherever observation happens to occur. There is a tension at the heart of understanding the Milky Way that never fully resolves. On one level, the galaxy is unimaginably large. Its span stretches across distances so vast that even light, moving without rest, takes tens of thousands of years to cross it. Hundreds of billions of stars orbit within its gravitational reach. Entire histories unfold inside it, layered over timescales that far exceed human experience. For any mind shaped by life on a planet, this scale is overwhelming. And yet, on another level, the Milky Way is small. Placed within the context of the observable universe, it becomes negligible. One galaxy among hundreds of billions. One luminous patch within a structure so large that individual galaxies vanish into statistics. The same object that feels boundless from within becomes almost invisible from far enough away. This is the scale paradox. The Milky Way is simultaneously enormous and insignificant, and both descriptions are accurate. The difficulty lies not in the facts, but in holding them together without forcing one to cancel the other. Human intuition is poorly equipped for this. The mind prefers a single frame of reference. It wants to decide whether something is large or small, important or trivial. It struggles when size depends on perspective, and meaning shifts with distance. The Milky Way exposes this limitation clearly. Locally, the galaxy defines everything. Every star visible to the naked eye belongs to it. Every planet ever observed directly or indirectly orbits a star within it. The night sky is shaped by its structure. From Earth, the Milky Way is not one object among many. It is the environment itself. From that position, calling the galaxy small feels absurd. Its scale dwarfs all familiar measures. No mountain, no ocean, no planetary system compares. The galaxy is the largest coherent structure most people ever meaningfully encounter. It becomes the upper bound of imagination by default. But the universe does not stop there. As the view widens, the galaxy's status begins to erode. Other galaxies appear, groups and clusters form, filaments stretch across enormous distances. The Milky Way shifts from being the whole to being a part. Eventually it becomes a point. Nothing about the galaxy has changed. Only the frame has. This is where cognitive dissonance emerges. The Milky Way cannot be both overwhelming and negligible at the same time, intuition insists. Yet it is. The contradiction is not in the galaxy, but in the assumption that size has a single, absolute meaning. In physics, scale determines relevance. At the scale of planets, galaxies are irrelevant. At the scale of galaxies, planets disappear. At the scale of the universe, galaxies themselves fade into background structure. Each level obeys the same laws, but different features dominate. The Milky Way matters profoundly at some scales and not at others. It matters when discussing star formation, stellar evolution, chemical enrichment, and the emergence of planetary systems. It does not matter when describing the expansion of the universe, the distribution of matter on the largest scales, or the geometry of space-time itself. This selective importance can feel unsettling. It suggests that significance is not inherent, but contextual. That an object's meaning depends on the questions being asked. The Milky Way is not always important, and it is not always trivial. It is important where it has influence. Understanding this resolves the paradox without eliminating mystery. The Milky Way is not large or small in isolation. It is large relative to human scales and small relative to cosmic ones. Both statements are precise, not poetic. The difficulty arises because the mind resists switching frames. There is an emotional pull toward treating the largest familiar structure as the ultimate one. For centuries, that role belonged to Earth, then the Sun, then the Milky Way. Each time the boundary moved outward, something that once felt final became provisional. This pattern continues. The Milky Way feels final only because it is where intuitive scaling fails. Beyond it, numbers stop helping. Distance loses texture. The galaxy becomes a psychological horizon rather than a physical one. Cosmology quietly moves past that horizon. It treats the Milky Way as one data point among many, not because it dismisses the galaxy, but because the questions change. When measuring the large-scale structure of the universe, the identity of any single galaxy is irrelevant. What matters is how matter behaves collectively. This can feel like reduction. A richly structured system becomes a dot on a map. A galaxy full of stars becomes a statistical entry. But this reduction does not destroy information. It filters it, preserving what matters at that scale. There is no contradiction here. The same object can be described in multiple ways without any one description being false. The Milky Way is a complex dynamic galaxy. It is also a negligible contributor to the universe's total mass distribution. These facts coexist without conflict. What gives the paradox its emotional charge is attachment. The Milky Way is home. It is familiar even if its details are not. Reducing it to a data point can feel like erasure, as though meaning is being stripped away by scale. But meaning is not scale invariant. Human meaning arises locally. It is tied to proximity, interaction, and experience. The universe does not distribute meaning evenly. It distributes matter and energy. Meaning is layered on top by observers. From that perspective, the paradox softens. The Milky Way does not need to be important to the universe to be important to those within it. Its lack of cosmic privilege does not diminish its role as the setting for every known experience. The galaxy is vast enough to dwarf human history and small enough to vanish into the cosmic web. Both truths deepen understanding rather than weaken it. There's also a quieter mystery embedded here. Why does scale behave this way at all? Why does importance fade smoothly rather than ending abruptly? Why does the universe allow structure at many levels without privileging any one of them? Physics provides partial answers. Gravity organizes matter hierarchically. Expansion sets limits on influence. Local forces dominate locally. Global behavior emerges globally. No single scale is final, because no single force dominates everywhere. But the lived experience of this remains strange. The Milky Way feels immense because it is immense relative to bodies and lifetimes. It feels small because it is small relative to the full extent of what exists. The mind must stretch to accommodate both without resolving them into a single narrative. This stretching is not meant to be comfortable. Astronomy does not exist to reinforce intuition. It exists to test it. The scale paradox is one of the clearest examples of this. It forces a recognition that understanding depends on context, and that truth can be layered rather than singular. The paradox also reframes curiosity. Instead of asking whether the Milky Way is large or small, the more revealing question becomes why it feels large in one frame and small in another. The answer lies not in the object, but in the observer's position within a hierarchy of scales. Seen this way, the paradox is not a problem to solve. It is a feature to notice. The Milky Way invites two kinds of awe at once, one grounded in direct scale, the other in comparative insignificance, one rooted in presence, the other in perspective. Neither cancels the other. They coexist, held together by the simple fact that the universe does not align itself with human intuition. It allows structures to be locally overwhelming and globally negligible, without contradiction. This coexistence is where the quiet mystery remains, not in whether the Milky Way matters, but in how easily meaning shifts with distance, in how smoothly the universe transitions from richness to abstraction, in how scale changes not just what is seen, but what questions make sense to ask. The Milky Way does not resolve into a single identity. It remains vast enough to humble the mind and small enough to disappear into statistics. It remains a home and a data point, a structure and a sample, a galaxy and a coordinate. That tension does not demand resolution. It invites patience, because the universe is not asking to be reduced to one perspective. It is asking to be understood at many, each one true within its own scale, each one incomplete on its own. And in that layered understanding, the scale paradox becomes not a contradiction, but a quiet acknowledgement of how limited any single frame of view must always be. As the view stretches outward, a final boundary comes into focus, not a physical edge, and not a place that can be reached, but a limit on what can be known with confidence. Astronomy often gives the impression of steady conquest, of ignorance replaced piece by piece with certainty. In reality, knowledge grows alongside uncertainty. Each answer exposes new questions, and each measurement carries limits that cannot be removed. Uncertainty is not a flaw in cosmology. It is a feature of how the universe reveals itself. Observations are made from a single location, using light that has travelled for immense spans of time. Instruments are powerful, but finite. Models are precise, but incomplete. What is known rests on layers of inference, each carefully tested, each constrained by what can be observed. This is especially true when discussing scale. Distances to stars and galaxies are not measured directly in most cases. They are inferred through chains of methods, each relying on assumptions that are well supported but never absolute. Small uncertainties compound as scale increases. A tiny error nearby becomes a large ambiguity far away. The Milky Way itself illustrates this clearly. Its overall size is known only approximately. The diameter of the stellar disk, the extent of the halo, and the reach of its dark matter envelope all depend on how boundaries are defined and how faint structures are detected. There is no sharp edge where the galaxy ends. There is only a gradual thinning, a fading into surrounding space. Even the galaxy's mass remains uncertain. Stars can be counted only indirectly. Gas clouds are traced through emission that depends on temperature and composition. Dark matter is inferred from motion rather than seen directly. Each method agrees broadly, but none delivers a single exact number. The result is a range, not a point. These uncertainties do not signal confusion. They signal honesty. Science does not pretend to know more than evidence allows. Where measurements converge, confidence grows. Where they diverge, caution remains. The boundaries of knowledge are marked clearly, not glossed over. On larger scales, the limits become more pronounced. Beyond the Milky Way, distances to other galaxies depend on cosmic distance ladders, redshift measurements, and models of expansion. These tools are powerful, but they rely on calibration. Each rung of the ladder depends on the reliability of the one below it. Improvements refine estimates, but they do not eliminate uncertainty entirely. At the larger scales, observation itself imposes absolute limits. The observable universe is bounded by the speed of light and the age of cosmic expansion. Regions beyond the cosmic horizon cannot be observed, not because of technical limits, but because of physical law. No future instrument can retrieve information from beyond that boundary. This creates a clear line. Everything within the observable universe can, in principle, be studied. Everything beyond it cannot. Models may suggest what lies beyond, but observation cannot confirm it. That distinction matters deeply in cosmology. It means that some questions are not unanswered, but unanswerable. How large the universe truly is beyond what can be observed, whether it is finite or infinite, what lies beyond the observable horizon. These are questions constrained by physics itself, not by lack of effort or imagination. Even within the observable universe, some features resist full understanding. The nature of dark matter remains unknown, its effects are measured precisely, but its composition is still uncertain. Dark energy, which drives accelerated expansion, is described mathematically but not explained fundamentally. These are not small gaps. They shape the universe's largest behaviors, and yet cosmology remains robust. The presence of unknowns does not weaken what is known. Models accurately predict observations across vast ranges of scale. Independent measurements converge on consistent values. The framework holds even as details remain unresolved. This balance is essential. Science advances not by eliminating uncertainty, but by bounding it. Each uncertainty is defined, constrained, and tested against observation. What remains unknown is not a failure. It is a map of where understanding has not yet reached. There is temptation to treat uncertainty as absence. To imagine that if something is not known precisely, it is barely known at all. This is a misunderstanding. Most scientific knowledge exists within ranges, not absolutes. Confidence grows through agreement, not exactness. The Milky Way's edges exemplify this. There is no single answer to where the galaxy ends. Different definitions produce different boundaries. The stellar disk fades, the halo extends farther, the dark matter envelope reaches farther still. Each description is valid within its own context. This layered structure resists simplification. It does not allow a clean outline. It reflects how gravity organizes matter gradually rather than abruptly. The galaxy blends into its environment rather than stopping. Cosmology is filled with such gradients. Clusters do not have precise borders. Superclusters dissolve into filaments. Filaments fade into voids. The universe does not divide itself neatly. Measurement must adapt to this reality. The limits of knowledge are therefore not walls but transitions, places where precision gives way to probability, where description shifts from exact to statistical, where certainty is replaced by confidence intervals rather than answers disappearing altogether. This is why uncertainty does not undermine scientific understanding, it strengthens it. By acknowledging limits, science avoids overreach. By stating where models apply and where they do not, it preserves reliability. Claims are matched to evidence, not ambition. There is also a deeper implication here. Uncertainty keeps curiosity alive. If the universe were fully known, exploration would end. Instead, each boundary invites refinement. Each unknown motivates new observation, new theory, new instrumentation. Even so, restraint remains essential. Not every question will be answered. Not every mystery will yield. Some limits are permanent. The cosmic horizon will never be crossed observationally. Certain early conditions may never be reconstructed fully. Some aspects of cosmic origin may remain forever indirect. Accepting this is part of scientific maturity. Knowledge does not promise completeness. It promises coherence. It promises that what is claimed fits what is observed, and that contradictions are resolved by revision rather than denial. The Milky Way once again sits comfortably within this framework. Much is known about its structure, motion, and history. Much remains uncertain. Its past mergers, its exact mass distribution, and the full extent of its halo continue to be refined. None of this diminishes the validity of what has been learned. Instead, it situates the galaxy properly, not as a solved object, but as a system understood within limits, not as a mystery without answers, but as a structure whose answers arrive gradually. Cosmology does not seek finality. It seeks accuracy within constraints. It seeks models that work where they apply and remain silent where they do not. This discipline is what allows understanding to expand without collapsing under speculation. In this sense, uncertainty is not a weakness. It is a signal that science is functioning as intended, that it distinguishes between what is known, what is suspected, and what is unknown, that it does not confuse curiosity with certainty. The vastness of the universe guarantees that limits will always exist. No perspective captures everything. No scale resolves all questions. Each widening of view reveals new boundaries alongside new insights, and that, perhaps, is the final perspective. The universe is not fully knowable, but it is deeply understandable within its limits. The Milky Way is not fully mapped, but it is meaningfully described. The cosmos does not offer complete answers, but it offers coherence. The limits of knowledge do not diminish wonder, they preserve it. Because beyond every carefully drawn boundary lies not failure, but the quiet recognition that understanding has edges, and that those edges are where curiosity remains most alive. All of human experience unfolds inside a single galaxy. Every story ever told, every thought ever formed, every moment of fear or wonder has occurred within one small region of the Milky Way's vast disk. Not at its centre, not near its edge, just somewhere inside, carried along by gravity and time. This fact is easy to state and difficult to absorb. The Milky Way is not a backdrop. It is the environment in which all familiar existence takes place. Its stars provided the raw materials for planets. Its long history allowed heavy elements to accumulate. Its stable orbit through space gave time for complexity to emerge. Life did not arise despite the galaxy, it arose within it. And yet, when the view expands far enough, that same galaxy becomes small. It fades into a single point among billions. Its influence ends long before the larger structures begin. The Milky Way does not shape the universe. It participates in it quietly, locally, without authority or reach beyond its immediate surroundings. Living inside something so small can feel unsettling. There is a tendency to equate size with significance, to assume that importance must scale upward, that being small implies being trivial, and that cosmic insignificance threatens meaning itself. Astronomy challenges this assumption without apology. Earth is not large by any cosmic measure. It is a planet orbiting an ordinary star in a typical spiral galaxy, located in an unremarkable region of space. Nothing about its position is privileged. Nothing about its scale commands attention from the universe at large. And yet, meaning is not diminished by this. Meaning does not arise from cosmic prominence. It arises from relationships, processes, and experience. Earth's smallness does not erase its richness. The fact that the universe does not revolve around it does not make what happens there less real. Astronomy sharpens this distinction. By revealing scale honestly, it separates importance from centrality. It shows that significance is not awarded by size or position, but by context. The universe is vast and indifferent, but that indifference does not negate the emergence of complexity within small regions. Living inside the Milky Way provides a rare balance. On the one hand, the galaxy is large enough to inspire awe. Its star-filled structure dwarfs human timescales. Its slow motion through space reminds observers that history is not measured only in lifetimes or civilizations. The galaxy carries memory on a scale that resists narrative. On the other hand, the galaxy is small enough to be contextualized. It is not the whole. It does not dominate. It belongs to larger patterns that reduce its apparent importance without erasing its existence. This tension invites reflection rather than despair. Astronomy offers perspective, not comfort. It does not promise that humanity is central or necessary. It does not imply that the universe cares about observation. What it does offer is clarity about where existence sits within a much larger framework. This clarity can be grounding. Knowing that Earth is small removes unrealistic expectations. The universe is not arranged for convenience or reassurance. It does not assign meaning based on scale. It allows meaning to emerge locally, without endorsement or opposition. This is not nihilism, it is restraint. Understanding scale does not tell anyone what to value, it tells them what not to assume. It removes the idea that importance must be cosmic to be real. There is calm in this realization. The Milky Way does not need to be large relative to the universe to be vast relative to human life. Earth does not need to be significant to the cosmos to matter to those who live there. These are not compromises. They are acknowledgements of how perspective works. Astronomy trains the mind to hold multiple truths at once. The galaxy is immense and ordinary. Earth is small and meaningful. The universe is indifferent and structured. None of these statements cancel the others. Living inside something small encourages humility. Not the performative kind, but the quiet recognition that existence is local. That understanding is bounded, that no single perspective captures the whole. This humility is not submission, it is orientation. It allows thought to settle. Questions about purpose shift. Instead of asking why the universe exists for observers, attention turns to how observers exist within the universe. The difference is subtle, but it changes the tone of inquiry from demand to curiosity. There is also a gentle liberation here. If Earth is not the center, then it is not under scrutiny. If the Milky Way is not special, then neither is its location. Existence does not require justification to the universe. It simply unfolds where conditions allow it. Scale reshapes thought by dissolving false hierarchies. Large does not mean important. Small does not mean insignificant. Central does not mean meaningful. Peripheral does not mean empty. These associations belong to intuition, not to nature. Nature operates differently. It allows vastness without purpose and complexity without intention. It permits meaning to arise in small places without announcing it on large scales. It does not broadcast value. It allows it quietly. Living inside the Milky Way means living inside this reality. A reality where the night sky is filled with stars that do not notice observation, where the galaxy turns slowly, unconcerned with thought, where life emerges briefly, locally, without altering the cosmic balance. This does not make life fragile in a cosmic sense. It makes it precise. Every experience occurs at the intersection of countless conditions that did not need to align, but did. That alignment is rare locally and irrelevant globally. Both are true. Astronomy does not ask observers to feel small. It asks them to feel placed within a galaxy, within a group, within a web, within an observable universe bounded by time and light. Each layer adds context without demanding interpretation. The calm comes from acceptance. Acceptance that the universe is large enough to dwarf everything familiar. Acceptance that familiarity still matters where it exists. Acceptance that understand in scale does not flatten experience, but deepens it. Living inside something small changes how questions are asked. Instead of searching for cosmic validation, attention turns inward to understanding. Instead of measuring worth by size, curiosity shifts to process. Instead of seeking meaning in the structure of the universe, meaning is recognized as something that emerges within it. The Milky Way remains a quiet home in this picture, not special by position, not dominant by scale, but sufficient. Large enough to contain histories, stable enough to allow thought, small enough to disappear when perspective widens, and that disappearance is not a loss. It is a reminder that existence does not need to be large to be complete. Living inside something small does not shrink thought. It steadies it. Because once scale is understood, the need for cosmic importance fades, replaced by a quieter awareness of where existence actually happens, here, inside one galaxy, inside one moment, inside a universe that does not center on experience but allows it anyway. The Milky Way is large in a way that resists ordinary thought, not metaphorically large, not poetically vast, large in a literal physical sense that overwhelms the tools the human mind uses to judge distance, duration, and separation. Even when the numbers are known, even when the measurements are stated clearly, comprehension does not follow easily. The galaxy stretches across distances so great that light, the fastest signal available, requires tens of thousands of years to cross from one side to the other. That fact alone is enough to unsettle intuition. Nothing in daily experience prepares the mind for delays measured not in seconds or lifetimes, but in civilizations. Within that span, hundreds of billions of stars move in slow, patient orbits. They do not cluster tightly. They are separated by vast gulfs of empty space. Even within the dense regions of the galactic disk, stars are typically light years apart. The Milky Way is not crowded in the way images sometimes suggest. It is spacious beyond any terrestrial analogy. This spaciousness is where intuition begins to fail. The mind is comfortable with large numbers when they describe collections. 1 billion grains of sand can be imagined as a heap. 1 billion people can be imagined as a crowd, but 1 billion stars spread across tens of thousands of light years do not form a picture the brain can hold. Distance, not quantity, is the obstacle. The galaxy's size is not just a matter of how much exists, but how far apart everything is. The emptiness between stars dominates the structure. Most of the Milky Way is not luminous. It is dark space threaded with occasional points of light. This emptiness is difficult to accept emotionally. Human environments are dense by comparison. Even the most remote landscapes on Earth are packed with matter. In the galaxy, emptiness is the norm. Stars are islands separated by oceans far larger than anything experienced locally. Because intuition fails, astronomy relies on mental tools. Comparisons are used even when they're known to be imperfect. Time becomes distance. Light years replace kilometers. Motion replaces scale. Orbits that take hundreds of millions of years substitute for direct measurement. These tools do not create understanding in the ordinary sense, they create orientation. They allow the mind to recognize that something exists beyond its grasp without pretending to fully imagine it. The Milky Way becomes known as a structure rather than pictured as a whole. For its inhabitants, however, the galaxy is complete. Every star visible to the naked eye belongs to it. Every planetary system discovered so far orbits within it. The Milky Way contains all direct experience of the wider universe. From the inside, there is no obvious indication that it is only one galaxy among many. To any civilization confined within it, the Milky Way could function as an entire universe. Its stars provide light. Its structure defines the sky. Its long time scales dwarf cultural memory. Without external reference, there is nothing to suggest that existence extends beyond it at all. This inward completeness deepens the paradox of scale. A structure that functions as a universe locally is, in a broader context, just one small component. The Milky Way is large enough to be everything to those inside it, and small enough to disappear when the view expands. This duality is emotionally complex. Encountering immensity often provokes a mixture of awe and unease, awe at the sheer extent of what exists, unease at the realization that familiar reference points do not scale upward. The Milky Way triggers both responses simultaneously. Awe arises naturally. The galaxy's age exceeds that of complex life by billions of years. Its stars recycle matter across generations. Heavy elements forged in ancient explosions become part of later systems. The Milky Way is not static. It is a long, ongoing process. Unease arises just as quietly. The galaxy does not acknowledge observation. Its motion continues regardless of attention. Its scale renders individual lifetimes almost invisible. It invites reflection without offering reassurance. These emotional responses are not errors. They are reasonable reactions to encountering scale honestly. The mind evolved to navigate environments measured in meters and years. When confronted with distances measured in light years and times measured in millions of years, discomfort is expected. Astronomy does not resolve this discomfort. It clarifies it. By stating plainly that the Milky Way is too large to be fully imagined, astronomy removes the pressure to imagine it. Understanding does not require visualization. It requires acceptance of limits. This acceptance changes the tone of thought. Instead of trying to compress the galaxy into a mental picture, attention shifts to relationships, how stars move, how matter is distributed, how gravity shapes structure. These processes can be understood even when the whole cannot be held in mind. The galaxy becomes knowable without becoming familiar. This distinction matters. Familiarity suggests intimacy. Knowability suggests structure. The Milky Way is not intimate. It is vast and impersonal, but it is structured, governed by principles that can be described and tested. For those living inside it, this structure provides context. The Sun's slow orbit around the galactic center situates planetary history within a larger motion. The distribution of stars explains why the night sky looks as it does. The presence of gas and dust explains how new stars continue to form. These connections ground experience. They do not make the galaxy smaller. They make existence more legible within it. Still, the Milky Way remains too large for the mind in a literal sense. No diagram captures it fully. No simulation conveys its lived scale. Even the most detailed maps are abstractions, compressions of reality into something manageable. This is not a failure of representation. It is a consequence of scale. Some structures exceed the capacity of imagination by orders of magnitude. The Milky Way is one of them. It must be approached indirectly, through fragments and relationships rather than through total vision. There is humility in this approach. It acknowledges that understanding does not require mastery, that knowledge can coexist with incompleteness, that the universe does not need to be fully pictured to be meaningfully understood. The emotional response to this humility varies. For some, it brings discomfort, a sense of smallness that feels diminishing. For others, it brings relief. The pressure to be central dissolves. The expectation of comprehension relaxes. Both responses are valid. The Milky Way is immense enough to unsettle and structured enough to invite study. It does not demand a single emotional posture. It allows reflection without instruction. What matters is that immensity is encountered without distortion, not inflated into drama, not softened into comfort, simply stated as it is, large enough to exceed imagination, coherent enough to be understood in parts. The galaxy does not ask to be grasped as a whole. It exists whether or not it is imagined correctly. Its stars will continue to orbit. Its gas will continue to collapse and ignite. Its slow rotation will continue to carry systems along vast paths through space. Understanding scale reshapes thought here. It replaces the urge to picture everything with the patience to accept limits. It replaces the need for familiarity with respect for distance. It replaces the expectation of centrality with orientation within something larger. The Milky Way becomes what it truly is, not a backdrop, not a symbol, not a metaphor, but a physical structure of staggering size governed by gravity, shaped by time, and inhabited briefly by observers who can know it without ever fully imagining it. This is not a deficit. It is a boundary that gives shape to understanding. The galaxy is too large for the mind, but not too large for knowledge. Too vast to picture, but not too vast to describe. Too immense to feel fully, but not too immense to matter locally. That balance is where the quiet response to immensity settles, not in fear, not in exaltation, but in recognition. Recognition that some things are not meant to fit inside thought. They are meant to surround it. When the view pulls back far enough, the Milky Way begins to disappear, not physically but conceptually. Its spiral arms blur, its vast disk collapses into a single point of light. The structure that once felt like an entire universe becomes one object among an uncountable number of others. Nothing about the galaxy has changed. Only the scale of comparison has. The universe is not built around galaxies like the Milky Way. It contains them in abundance. Hundreds of billions fill the observable cosmos, scattered across filaments and clusters, each following its own history. Some are larger, many are smaller. Most are different in detail, but similar in essence. The Milky Way is neither rare nor dominant. It is typical. This realization is not dramatic. It arrives quietly, through accumulation of evidence rather than revelation. Galaxy surveys reveal no thinning of numbers with distance. Deep observations show galaxies wherever the universe is transparent enough to see. There is no region where the Milky Way's kind suddenly gives way to emptiness. The universe is an environment, not a stage. Galaxies do not sit at its center or define its structure. They inhabit it the way organisms inhabit an ecosystem. Numerous, distributed, shaped by shared rules rather than unique roles. In this environment, size alone carries no authority. A larger galaxy does not control the universe around it. A smaller one is not dismissed by physical law. Gravity operates locally. Expansion operates globally. No single galaxy, regardless of mass, alters the behavior of the universe as a whole. The Milky Way's gravitational influence ends quickly. Beyond its halo, its pull fades into insignificance compared to the collective mass of surrounding structures. It does not guide the motion of clusters. It does not shape the cosmic web. It does not matter to expansion itself. This is not a criticism. It is a description of scale. The universe is vast enough that even enormous structures become small within it. Galaxies are meaningful locally, but globally they are statistical elements. Their individual stories do not register in the largest patterns. This shift can feel jarring. The mind invests heavily in what is familiar. The Milky Way feels special because it contains everything known directly. Reducing it to a point on a map can feel like loss, as though something intimate has been rendered irrelevant. But irrelevance is not what is happening. The Milky Way does not lose its complexity or its history when placed in cosmic context. It loses only the illusion of centrality. The universe does not revolve around it, but neither does it erase it. Cosmic scale is neutral. It does not elevate and it does not diminish. It does not assign importance based on size. It allows structures to exist where conditions permit and places no additional weight on their presence. This neutrality is easy to misinterpret. Indifference can be mistaken for emptiness. Lack of preference can be mistaken for lack of meaning. But the universe's neutrality is not a statement about value. It is a statement about process. Processes do not care. They operate consistently everywhere. Gravity pulls, space expands, matter clumps, energy dissipates. None of this is directed. None of it is responsive to significance. Within that neutrality, galaxies form. Within galaxies, stars ignite. Within stars, elements are forged. Within those elements, planets arise. Within a few of those planets, conditions align briefly enough for awareness to emerge. The universe does not notice this chain, but it allows it. This allowance is enough. The Milky Way being small relative to the universe does not reduce the improbability of what happens inside it. If anything, it sharpens it. In an environment of countless galaxies, only a fraction host planets. Of those, fewer still host life. Of those, fewer still host observers capable of reflection. Cosmic abundance does not cheapen local rarity. It frames it. The paradox that once seemed troubling now resolves gently. The Milky Way is too large for the mind when considered from within, and too small for the universe when considered from without. These are not conflicting truths. They are complementary perspectives applied at different scales. Wonder does not diminish when size loses authority. It changes character. Instead of being anchored to dominance or centrality, wonder shifts towards structure, emergence, and coherence. The universe becomes remarkable, not because it centers on anything familiar, but because it produces familiarity at all. There is calm in this realization. The universe is not organized around importance, it is organized around consistency. That consistency allows complexity to arise without permission or recognition. It allows small places to matter intensely without needing to matter universally. The Milky Way fits perfectly into this picture. It is one galaxy among many, moving quietly through an expanding cosmos. It does not anchor anything larger than itself. It does not need to. Its role is local, and local roles are where experience happens. From a cosmic distance, the galaxy vanishes into background structure. From within it, the galaxy is everything. Both views are accurate, neither cancels the other. They coexist without tension once scale is acknowledged as the deciding factor. This is where the paradox truly settles. Not by declaring one perspective correct and the other mistaken, but by recognizing that scale determines relevance. What matters nearby does not need to matter everywhere. What is small globally can still be vast locally. The universe is large enough to hold both truths without contradiction. The Milky Way remains small relative to the universe, and immense relative to human life. The universe remains indifferent to both. Wonder persists, not because anything is privileged, but because coherence exists across scales that do not acknowledge one another. In that coherence, the galaxy's smallness is not a reduction, it is a placement, placed among countless others, placed within patterns that extend far beyond it, placed in a universe that does not single it out, yet allows everything within it to unfold. The universe does not need the Milky Way to be large, it needs only to be consistent. And within that consistency the galaxy continues on, modest in scale, rich in detail, neither central nor erased, simply one structure among many in an environment vast enough to make size itself a relative concept. Too small for the universe, still large enough to hold every story ever known, and that balance is not a loss of wonder. It is the form that wonder takes when scale is understood honestly. There is a way of seeing the universe that does not demand resolution. It does not ask for a final scale to be chosen, or for one perspective to outweigh another. It allows different frames to exist together, each accurate within its own context, none elevated into a hierarchy. The Milky Way fits naturally into this way of seeing. It is immense when considered from within, vast enough to overwhelm intuition, structured enough to take light tens of thousands of years to cross, rich enough to contain hundreds of billions of stars and the long histories written into their motion, and at the same time it is small, not metaphorically small, physically small when placed against the observable universe. One galaxy among hundreds of billions. One localized structure embedded in patterns so large that individual galaxies fade into background texture. Holding both views at once is not contradictory, it is simply accurate. The difficulty comes from a habit of ranking, the tendency to decide which scale is the real one, which perspective deserves authority. Astronomy quietly dissolves that habit. It shows that scale is not judgment, it is context. The Milky Way is not diminished by being small in a larger frame, nor is it exaggerated by feeling vast locally. Its size does not change, only the questions change. When the question is about star formation, planetary systems, or chemical history, the Milky Way is an enormous and complex system. When the question is about cosmic expansion or the distribution of matter across the universe, the Milky Way becomes one data point among many. Neither view corrects the other, they coexist without conflict. This coexistence is something astronomy teaches indirectly, not through instruction, but through exposure. Each widening of perspective reveals that meaning does not scale in simple ways. Large things are not automatically important. Small things are not automatically trivial. Relevance depends on where attention is placed. The galaxy becomes both home and speck. Home, because it contains everything familiar, every night sky, every planetary orbit, every history of life and thought. Speck, because its influence ends quickly when compared to the full reach of the universe. This dual identity does not need to be resolved. Trying to resolve it often introduces distortion. Either the local view is inflated into cosmic importance, or the cosmic view is allowed to flatten everything into insignificance. Both moves oversimplify. Scale is not an argument. It does not declare what matters. It describes relationships. The Milky Way matters locally because local processes happen within it. It does not matter globally because global behavior is governed by forces and distributions that do not depend on any single galaxy. Understanding this removes pressure. There is no requirement for the Milky Way to be special in order to be meaningful. There is no requirement for Earth to be central in order to be significant. Meaning does not travel upward with scale. Astronomy does not offer comfort in the traditional sense. It does not reassure by placing observers at the centre. but it does offer a steadier kind of clarity. It shows that existence does not need cosmic validation to be real. The universe does not rank locations. It does not assign importance based on size, age, or position. It operates uniformly, allowing complexity to arise where conditions permit and remain local where it does. This uniformity can feel cold if interpreted as indifference, but it can also feel liberating. If no place is privileged, then no place is excluded. If no scale dominates, then no perspective is invalid by default. Local meaning is allowed to exist without justification to larger structures. The Milky Way exemplifies this permission. It does not need to be exceptional to be sufficient. It does not need to dominate the universe to contain everything that matters to those within it. Understanding scale reshapes thought quietly. It encourages restraint. It discourages grand conclusions. It replaces the urge to finalize with the patience to hold multiple truths without forcing them together. This is why perspective does not end in conclusion. There is no final statement that resolves scale once and for all. No single framing that makes all others unnecessary. Each perspective answers certain questions and leaves others untouched. Astronomy respects this incompleteness. It does not close the universe into a single narrative. It allows openness to remain not as a failure, but as an honest reflection of how understanding works. The Milky Way remains suspended between scales, too large to be grasped fully, too small to define the universe, vast enough to inspire awe, modest enough to disappear when perspective widens. This suspension is not unstable. It is balanced. It allows the galaxy to be known without being elevated. It allows the universe to be vast without being overwhelming. It allows thought to move freely between scales without being trapped by any one of them. What astronomy quietly teaches about place is subtle. Place is not about importance. It is about relation. Where something sits determines which forces act on it, which structures surround it, and which questions apply. Earth's place is local. The Milky Way's place is galactic. The galaxy's place is cosmological. None cancels the others. Perspective becomes a tool rather than a verdict. It allows observation without judgment. It allows understanding without finality. It allows wonder to persist without needing to be justified by scale. Ending without conclusion is appropriate here. The universe does not conclude. It expands. Structures evolve. Perspectives widen. Boundaries shift. Knowledge grows and uncertainty remains alongside it. The Milky Way will continue its slow rotation. Stars will form and fade. The galaxy will move through space, unchanged by observation, carrying its contents along paths measured in millions of years. Understanding this does not demand a final thought. It invites a settled one, a recognition that scale provides context, not hierarchy, that being small does not negate meaning, that being vast does not grant authority. The Milky Way can be held as both home and speck without tension. The universe can be vast without diminishing what happens locally, and perspective can widen without closing anything behind it. There is no need to arrive at an answer that ends the thought, only to remain aware that where something is seen from determines what it appears to be, and that this awareness, once gained, does not fade. It stays quietly present, like the galaxy itself, turning, unconcluding, still there,